it is around 10 10 a.m. there, sir, Hungary. So thank you so much, sir, once again that you have you agreed to provide your valuable lecture. I think our participants will learn many things from you about organophosphorus chemistry, and related, and how you involved some greener tools to design some organophosphorus compounds. So, dear participants, let me introduce Professor Keklevich. This is the 9th scientific lecture. The topic of this lecture is meeting of two disciplines: organophosphorus chemistry and green chemistry. And Professor George Keklevich is a senior professor of Department of Chemistry and head of the department, Budapest University of Technology and Economics, Budapest, Hungary. Let me tell you about little short introduction about Professor Keklevich. Professor Keklevich graduated from Technical University of Budapest in 1981 as a chemical engineer. He was awarded the Doctor of Chemical Science degree in 1994 in the subject of organophosphorus chemistry. He was the head of the Department of Organic Chemistry and Technology in the period 1999 to 2021. So presently he is the head of the group Organic Chemical Technology. He is a phosphorus heterocyclic chemist. He also deals with environmentally friendly chemistry like microwave chemistry, phase transfer catalysis, and the development of new catalysts. He is the author and co-author of more than 680 papers. Can you imagine? I'm repeating once again, 680 research papers. He wrote around 35 book chapters, 60 review articles, authored 2 books. I'm thankful that I have also contributed 1 chapter in that book, Organophosphorus Chemistry Novel Developments. He is the editorial board member of so many scientific journals. All are in high impacted journals. He is the editor-in-chief of current green chemistry and current organic chemistry. So with this short introduction, I am again welcoming you, sir, in this international conference. And now you can please share your slide, because we have already made you the co-host. So now you can able to share your slide, and you can proceed with your lecture. Thank you, sir. Thank you once again.
Thanks, dear Chairman. Good afternoon to everybody. First of all, let me thank for the nice introduction. And
sir, can you please make it the full screen?
Right, but I cannot find the knob projecting. I cannot find the. Okay, it will be okay right now.
Yeah, now it is okay, sir. No, it's
okay. Okay. So first of all, let me welcome the chairman, Professor Bubun, and also all participants from Budapest, Hungary, Europe, where we have a pleasant late summer or pre-autumn weather. I am grateful to Professor Bubun for inviting me to deliver this plenary lecture. Well, we have been dealing with organophosphorus chemistry for a long time, and in the last 15 years, we mixed organophosphorus chemistry with green chemistry. I worked and I am working with excellent colleagues, including PhD students and students. I should like to give you a brief overview of our recent results. Here you can see the contents. First, I'm going to okay. Moment. First, I'm going to give you a brief overview on the esterification of phosphenic acid derivatives. I shall let you know the scope and limitations of the application of microwave chemistry. Then we will change for the esterification of phosphonic derivatives, hydrolysis of P esters, and interesting reactions like the Arbuzov reaction, the Kabachnik-Fields reaction, the deoxygenation of phosphinoxides, the Hirao reaction, Pudovic reaction, and finally, I am going to give you details on the synthesis attained in the preparation or in the optimization of dronic acid derivatives. So first of all, let me tell you something on the esterification on the preparation of phosphenic esters. Phosphenic esters are called phosphonates. One of our major model reactions is the synthesis of phosphonates. The classical version is the esterification of phosphenic chlorides with alcohols. You can see in the first line, esterification of phosphenic chlorides with alcohols. The problem with this reaction is that HCl is the side product, and also consequently it is not an atomic efficient reaction. From practical point of view, this is a disadvantage. The optimal solution would be if a phosphenic acid could be reacted with alcohols, but normally this kind of reaction just doesn't work. Here you can see this reaction. Normally there is no reaction between phosphenic acids and alcohols. But we were so lucky and brave that we tried this reaction under microwave irradiation, and it was wonderful that the esterification took place under microwave conditions in a pretty good way, and we could obtain the H-phosphenic acid derivatives sometimes, in most cases, in good yields. Then this kind of reaction was extended to other kinds of model compounds, and our favorites are the cyclic phosphenic derivatives, including phospholine oxides, right here, the 5-membered heterocycles prepared by the McCormack cyclic addition reaction of isoprene and phosphorus tribromide, followed by hydrolysis. So, and this model compound was subjected to esterifications under different conditions. As I mentioned, on conventional heating, there was practically no reaction, as at 200 centigrade after 2 hours, only 11% was the conversion. This is very poor. But on microwave irradiation at 200 centigrade at the same temperature, the conversion was already 62%, and we could isolate the corresponding phosphonate in almost 60%. And the next surprise was that adding some ionic liquid as a catalyst, not as a solvent, as a catalyst into the mixture, we could reach enormous quantitative conversion and even a better yield. And this reaction could be extended to other kinds of alcohols. And here you can compare the reactions carried out in the presence of ionic liquid, methylbutylimidazolium hexafluorophosphorate, or in the lack of this ionic liquid. And we learned that in the presence of ionic liquid, the reaction temperature could be lowered, the time became shorter, and at the same time, the conversions became much better. So it was really advantageous to use some kind of ionic liquid as the catalyst. Please note that during my lecture, I'm going to show you how to utilize microwave in from different aspects. In this way, a microwave is some kind of catalyst, and also ionic liquid is another kind of catalyst. It can be regarded to be a co-catalyst. And also, we could extend this kind of reaction for the esterification of other phosphorus heterocycles. Here you can see another methyl group. Here you can see a saturated ring. This is the phospholene oxide. This is the phosphorylene oxide, the dimethyl derivative comprising two diastereomers, and also the the corresponding six-membered heterocycles that is called hexahydrophosphine oxide. I mean the phosphinic acid derivative, the hydroxy derivative of it. And you can see that using the catalyst I mentioned in the previous slide, we can lower the temperature, we could shorten the reaction time, and the yield was increased in all cases. Moreover, we could establish a reactivity order. According to this, the saturated derivatives, the fully saturated derivatives, were of lower reactivity. But if there was some kind of double bond in the molecule, these were more reactive. It is obviously in connection with the partial positive charge on the phosphorus atom. If there are electron donating substituents, the partially positive charge will be smaller. In this case, the partial positive charge is more significant. Okay. And then we could extend this kind of reaction to other kind of alicyclic phosphinic acids, I mean for their esterification. And please observe that in the first model compound, there is only one phenyl group. In the second one, there is a methyl group instead of the hydrogen atom. And finally, there are two phenyl groups. And we found that in all cases, even in the sterically hindered model compound, we could achieve pretty good and efficient esterification in the presence of butyl-methyl imidazolium hexafluorophosphorate. 10% should be used. Please note that we are working in a very small scale, and in a very small scale, we have to use somewhat more catalyst. This is the reason that we didn't apply 5%, but we had to apply 10%. Increasing the size, of course, less catalyst could be enough. Here you can see the possible mechanisms for the esterification of a phosphinic acid. Of course, on the left side, you can see the classical mechanism, the textbook mechanism. This is completely similar with the esterification of carboxylic acids. What happens? First, the alcohol attacks, makes a nucleophilic attack on the phosphorus atom. Better to say, in the first step, the oxygen atom is protonated, and in the second step, the alcohol attacks the partially positive charged phosphorus atom. Then you can get this adduct, and after the proton transfer, it will lose this species, this intermediate will lose water, and then you get practically the ester. This is the traditional mechanism. At the same time, there is another kind of mechanism which was discovered by us and substantiated or by our team, including theoretical chemists. According to this, the addition is followed by a so-called pseudo-rotation. This is the pentavalent pentacoordinated species, and in organophosphorus chemistry, it is very common that this kind of species may undergo so-called pseudo-rotation. It means that the axial and the equatorial substituents, according to rules, may change their position. And this was so surprising that the four-membered transition state was formed, and via this four-membered transition state, we got the ester eventually. And of course, the deprotonation resulted in the final product. So in our theoretical calculations, this kind of four-membered transition state was assumed. That was substantiated by our theoretical colleagues. Okay, this is a very important transparency. Here I should like to show in which cases the microwave irradiation may be indeed useful. You can see three diagrams, very common diagrams showing typical reaction profiles. In the first case, there is indeed exothermic reaction. You see, exothermic reaction. There is a lot of energy gain. There are two sub possibilities. This exothermic reaction may go via low transition state, and it may go with a higher transition state. In the second case, there is no energy, practically there is no energy gain in the reaction. This is a so-called thermoneutral reaction. At the same time, the the activation barrier may be a normal one or maybe a higher one. And in the third case, again, there are two possibilities regarding the activation barrier, but these are endothermic reactions. And we found, and we published in several, in several of our papers, that microwave irradiation should be or may be typically applied for this kind of reactions in the middle that are practically thermoneutral and with a high enthalpy of activation. If the reaction is exothermic, there is practically no need for microwave irradiation because the reaction takes place by itself. And when the reaction is endothermic, endothermicity works against microwaves. So you will never be able to attain quantitative conversion. You will see examples when we applied microwave irradiation for this kind of compounds. The reaction took place only partially. So please know and memorize that microwave irradiation was practically found out and excellent for this kind of reactions with a high enthalpy of activation and that are practically thermoneutral. Okay. So let me illustrate this phenomenon with precise examples. Here you can see our favorite model compound, model reaction, when hydroxyphospholine was esterified with butanol under acidic conditions. And our quantum chemist calculated pretty high enthalpy of activation, comprising 135 kilojoule per mole. This is very, very high. Here you can see the four-member transition state I spoke about a few minutes ago. And as a comparison, we also calculated the activation parameters for a common esterification. The esterification of acetic acid is methanol. And you can see that here, indeed, the enthalpy of activation is much lower, only 75 kilojoule per mole. Okay, so this is the difference between the esterification of a common and garden variety carboxylic acid and that of a phosphenic acid. And here in the common esterification, there is no need for microwave irradiation, but this reaction, the esterification of phosphenic acids, may take place only on microwave irradiation. And I will elucidate what the reason of this phenomenon is, but please wait a little bit. Okay, it's a very interesting experience that we changed butanol to thiobutanol. And see that an oxygen atom was replaced by a sulfur atom. And this has a huge consequence on the huge impact on the course of the reaction, because we could not perform complete conversion. The reaction stopped at about 33%. And sure enough, the quantum chemical calculations, theoretical calculations showed that this is an endothermic reaction with a very high 145 kilojoule per mole enthalpy of activation. So no wonder that in this case, the conversion could not be turned to quantitative, because this is, as I mentioned, an endothermic reaction. And microwave irradiation is not so fine cannot help for endothermic reactions. But it's very interesting to compare the esterification with thiobutanol here with that of the esterification with butanol. One tiny difference, replacing the oxygen atom to sulfur or vice versa, results in such a great difference. It's very, very interesting. And also another example for endothermic reactions. Of course, it was very obvious for us to try the direct amidation reactions of phosphenic acid. And in this case, again, only a low conversion, incomplete conversion at approximately 30% could be achieved. Why? Because again, we had to face with an endothermic reaction. But in this case, the activation enthalpy is not so high, only approximately 80 kilojoule per mole. Still, endothermicity worked against the positive effect of microwave irradiation. So in this case, it remained for us to perform the preparation of the corresponding amides via the classical route, when phosphenic chloride is the starting material, and this is reacted with the amine, 2 equivalents of the amine or 1 equivalent of the amine together with 1 equivalent of the triethylamine in toluene, and in this case we could obtain the corresponding amides in pretty good yields after purification. Also, we prepared, and this is a fully new family of compounds, this kind of imides. This is an imide if you consider the analogous compound from organic chemistry, phosphorus imide, prepared by us for the first time. And also mixed imides could also be prepared by phosphorylating the phosphenic amides. These are again very new compounds that are of potential bioactivity. Later on, I'm going to speak about the bioactivity of our compounds prepared. Okay, so we arrived at a very important part. I should like to explain you, I should like to summarize and explain you the scope and limitations, the so-called scope and limitations of the application of microwave irradiation. Here it is confirmed that thermoneutral reactions with relatively high enthalpy of activation. What do I mean under high enthalpy of activation? I mean bigger or greater than 100 kilojoule per mole. Below 100 kilojoule per mole, there is no need for microwave irradiation. Above 100 kilojoule per mole, microwave irradiation may help if the reaction is indeed thermoneutral. Okay, so this is the first important point, first important criterion. The second criterion is how it works. I promised you that I will explain, and now I'm trying to explain the beneficial effect of microwave irradiation. Well, the beneficial effect is the consequence of the so-called local overheating effect. Local overheating effect. This is passive. The beneficial effect is possible is the consequence of the statistically occurring local overheating effects that may be in the range of 1 and 60 centigrade. It means that in the nano parts of the bulk of the mixture, there may be more heated segments, and the difference in the temperature may be between 1 centigrade. This is very often only 1 centigrade or less, and sometimes even there might be 50 or 60 centigrade difference in the bulk of the mixture. The latter one, the big difference is not so frequent, but this may be, this may occur. So, and these are very effective, this kind of overheatings, and these overheatings may involve 1 or 40% of the bulk of the mixture. So this is the explanation, and there is no magic effect at all. This is simply a local overheating effect that promotes the reactions and helps to overcome the high enthalpy of activation. Please imagine that you have to climb a high mountain. It is not so easy, but if you have some push, some help, it will be possible. And microwave irradiation, due to the local overheating effects, give this assistance. Okay, so this was on the esterification of phosphenic acids. Now let us turn for the esterification of phosphonic acids. What is the difference between phosphenic acids and phosphonic acids? Regarding phosphenic acids, there was only one alkoxy group, phosphenic esters. Regarding phosphonic esters, there are 2 alkoxy groups. So how to prepare phosphonic derivatives in a green manner? First, we tried another strange method, and phenyl H phosphenic acid was esterified. As I mentioned, I showed this example in one of the previous transparencies. We prepared these esters efficiently, and then we decided to oxidize this pH bond by metachloroperbenzoic acid, and indeed the oxygen was inserted between the phosphorus and the hydrogen atom, and this, please observe that this is already a mixed ester acid, and this mixed ester acid could be esterified under microwave conditions with alcohol. But I have to admit that the efficiency of this esterification was not so good. The conversions remained low, so we were satisfied with this method. We wish to elaborate a better one. And here you can see that we tried directly the esterification of phenyl phosphonic acid. Phenyl phosphonic acid, available commercially. This was the first model compound, and we heated it under microwave irradiation together with the catalyst ionic liquid. And sure enough, we could observe that the monoesters were formed in a pretty good conversion. Moreover, I can tell you that this reaction is rather selective, and chemists, you know, always like selective reactions, because the diester was formed only in a lower proportion, and by a simple cleaning method and chromatography, the monoesters could be isolated in pretty good yields. Of course, when we isolated these phosphenic ester acids, we tried to react them separately under microwave irradiation with alcohols. But this experience above was confirmed that only incomplete conversions could be obtained. So we were not too happy to conclude monoesterification is possible by microwave irradiation, but diesterification is not really possible. So we work together, we will work further, and we try to apply the so-called alkylating esterification. Alkylating esterification, here is the phosphenic acid, and butyl bromide was applied in the presence of one equivalent or two equivalents, depending on the molar ratio of the triethylamine as a base. And sure enough, this reaction could be fine-tuned. This reaction could be fine-tuned. If less of the reagents were applied, the monoester was the predominant component. If we applied more from the alkylating agent, then the diester was the predominating product. So fine-tuning was possible. So this was a good indication how to continue our work. Moreover, again, the monoesters were prepared in a trim form, and the monoesters were also subjected to alkylation esterification. And in this case, we could obtain the esters, the phosphonates. Phosphonic diesters are called phosphonates. The phosphonates could be obtained in pretty good yields. Moreover, it was also possible to introduce a different second alkyl group, you applying another kind of alkylating agent. You know, organophosphorus chemists are very keen of preparing phosphorus compounds with a chiral center. If there are 4 different substituents, this compound is chiral. It means that it can be separated to, if we have the suitable method, the racemic compound can be separated to 2 antipodes. Actually, we have also such experiences, but that could be a separate lecture. And if we remove the double-bonded oxygen atom, then you will get P ligand. And the chiral P ligand may be very valuable in different asymmetric synthesis, applying homogeneous catalysts involving palladium, platinum, rhodium, and so on. We have a lot of such experiences, but in this lecture, I'm not going to speak about these earlier results, of course. Okay, so how to conclude this kind of reaction? That was, in the meantime, extended also to other model compounds, and we published our new results in molecules together with new colleagues who work on this topic. So the conclusion is that if we wish to convert phosphonic acids, maybe in a general sense, phosphonic acids to phosphonic esters, the first step should be done by direct esterification, applying alcohol and ionic liquid as the catalyst. At the same time, the second step should be performed applying an alkylating esterification. Okay, so these 2 different kinds of steps mean an integral synthesis of phosphonates. And in this case, we don't have to use P chlorides. P chlorides are expensive, and their use is not atomic efficient. Let me tell you that in the first step, we used the alcohol in a 15-fold quantity, but no problem, because on distillation, the excess could be recirculated. So there was no waste regarding the alcohol. And the ionic liquid, we are trying to reutilize the ionic liquid of this used as catalyst. But as I mentioned, in the first approach, we perform the reaction on a very small scale, and the quantity of the catalyst is also 10%, is a very small, it means microliters in some occasions. Okay, so we proceeded further, and at our department there was a project to elaborate flow chemical synthesis, and of course we had the possibility of developing microwave assisted flow chemical synthesis. Microwave assisted flow chemical synthesis. Here is the SEM microwave reactor, and commercially it was available to purchase this kind of flow cell. This is the flow cell here, and my colleagues helped to construct this equipment. We had to apply HPLC pump and a back pressure regulator, and in this way the flow system was established. We chose a very simple reaction when we started this project 3 years ago. We chose the esterification of benzoic acid with different alcohols, and this system worked well, and then we could apply this flow system for more sophisticated reactions, such as the esterification of phenyl H-phosphenic acid. I mentioned this at least twice in the previous 30 minutes. So phenyl H-phosphenic acid could be esterified in this flow system efficiently using, you see, only 5% butylmethylimidazolium hexafluorophosphate at different temperatures between 160 and 200 centigrade, and with different flow rates. And it was found that this kind of synthesis is more efficient than preparing the ester, the phenyl H-phosphonate, in a batch reactor. So continuous synthesis was somewhat more efficient. And also the product ester, the ethyl ester, could be subjected to trans-esterification reactions. This is a new purpose in my group, to extend the scope of trans-esterifications and even transamidation reactions. I'm not going to speak about too much about this alcoholytic or trans-esterification reactions. By the way, trans-esterification, you know, it is a very interesting kind of reaction if you regard the scope of the preparation of biodiesel. The preparation of biodiesel in the European Union, you must add to the gas, to the petrol, 10%, even more than 10% of biodiesel or bioethanol to the fuels. So this means trans-esterifications and also alcoholysis of P esters are very, very important, because the methods may be of general value. So here is the trans-esterification of phenyl H-phosphenic acid, and this worked well, and we could again prepare efficiently this kind of esters. And in the past, we have studied also the trans-esterification of dialkyl phosphides. In this lecture, we shall return to the importance of dialkyl phosphides. In previous cases, we applied common alkoxy groups, but it occurred to us that benzyl derivatives may be much better, because it is more reactive. It is easier to remove benzyl group from this group, easier to replace by other alkoxy group. And sure enough, the reactions could be performed if also in batch and in continuous flow microwave assisted systems, and depending on the conditions, on the temperature, and on the molar ratio of the substrate and the alcohol, we could optimize this kind of reaction to obtain the mixed derivative. Please note that in this B derivative B, there are two different alkoxy groups, or the fully trans-esterified product at higher temperature, applying more alcohol. Okay, so species B are very valuable. We could optimize the rate proportion for at least 50%, and this is a value because from this mixture we could prepare the mixed derivatives again with a chiral phosphorus atom. I outlined the importance of this kind of chiral species. Okay, so please allow me to be a little bit theoretical right now, because we also performed a lot of work with my theoretical colleagues, how to predict, how to model the effect of microwave irradiation and how to predict the effect. So, how is it possible to model and calculate the thermal effect of the local overheatings? You all know the key is the local overheating effect. The other key is the Arrhenius equation. You can see here, it's very common physical chemistry, Arrhenius equation, that makes possible to calculate the actual rate constants in the bulk and also in the overheated nanosegments. The overall rate constant is the weighted sum of key bulk and the individual K values, the sum of the individual K values of the overheated segments. No, it is not so complicated. Modeling the thermal effect of microwaves is possible by assuming a percentage overheated segment. So we should estimate the percentage overheated segment, and assuming an exponentially decreasing, you see in the diagram, an exponentially decreasing relationship between the particular overheated segment and the overheating itself. This was, I mentioned, that regarding a smaller difference in the temperature is more probable, and assuming a big difference in the temperature like 60 centigrade or even 50 centigrade is not so probable. It may occur rarely only, but this has an overall effect on the course of the reaction. Regarding the proportion of the sum of the overheated segments, 5 cases, you can see in the left side, 5 cases were differentiated and applied to our favorite model compound. Within the 5 cases, distinct overheatings of 5, 10, 20, 30, 40, and 50 and 60 were assumed. The partial rate constants were calculated and weighted to give the relative accelerations. Here are the relative accelerations. And fancy that 3.1 was the relative acceleration from the experiments. It means that in this case, if the relative acceleration is 3.5, then we should assume that the 40% of the bulk suffered, in parentheses, suffered some kind of overheating. So it means that we could model, first in the literature, we could somehow, with assumptions, of course, we could model the effect of microwave irradiation. Okay, I take a big breath and let us continue with other kind of change of functionalities of organophosphorus compounds. So I have been speaking about esterifications. Now we are going to see the hydrolytic reactions. This kind of reaction, of course, the first model reaction was this cyclic phosphenic ester, ethoxyphosphorylane oxide, and we optimized it, and the hydrolysis was followed, is monitored with P31 NMR spectroscopy. That is a big possibility. P31 NMR spectroscopy is a fantastic tool, and also this was applied to the six-member species. Here you can see 2 product line because the product 4 comprising 2 diastereomers. Okay, in the literature there was a black box of this kind of reaction, no optimizations, no reasons, And we, together with an excellent PhD student, Ms. Arshagi, elaborated a lot of kind of versions for the hydrolysis. Here is the unsaturated version. It is a little bit more complicated because isomerization may also take place, and even ethyl esters were examined, and other kind of compounds, and we monitored the reactions, and even we could calculate these programs, of course, iterative programs, the key values, and we could compare the reactivity of the compounds. The fully saturated derivative was the less reactive, and again, the unsaturated derivatives were somewhat more reactive. And also, of course, phosphonic esters were also subjected to this kind of hydrolysis, and there is the intermediate with a acidic function and alkoxy group, OH group and alkoxy group, but the final product is the fully hydrolyzed phosphenic acid. And again, key constants were determined, and we found that the second step, you see there are two steps. The second step was the rate determining step, and it was also interesting that beside the AS2 mechanism, in some cases, for example, in the case of isopropyl derivatives, the AL1 fission was also substantiated. Okay, so very briefly, let me speak about the Arbuzov reactions. Here is an aryl bromide, and we wish to react it in Mikhail's Arbuzov reaction, but you know, aryl bromides are of lower reactivity. For this reason, nickel chloride is used in the literature, and we found that microwave irradiation may promote further this kind of reactions. Okay, we arrived at a very classical reaction, and this is the Kabachnik-Fields reaction. The products are aminophosphonic derivatives, and aminophosphonic derivatives are useful as can compete with natural amino acid derivatives, and we will interact with the enzymes and other parts in our organ, and antiviral, and the consequences antiviral and antibiotic and even anti-tumor effect. Okay, so the point is that in certain cases the catalyst may be substituted by microwave irradiation. A lot of catalysts have been applied, and we found that under microwave irradiation there is no need for environment polluting and even expensive catalysts. So in this case, microwave would substitute the sophisticated catalysts, and we worked a lot of we invested a lot of energy in this kind of reaction. Even the fourth PhD student is working on this kind of reaction, and we also found that amide could took part in this kind of three component reaction, but in this case the amide had to be applied in an excess, so this was a kind of solvolytic reaction. These are very interesting species regarding aminophosphonic derivatives. And also, let me tell you something on the deoxygenation reaction. Deoxygenations are rather important. Please consider just the Wittig reaction. The Wittig reaction produces triphenyl phosphenoxide as the byproduct, you know, and in earlier times it was burned, and it is a waste. So of course it is much better if triphenyl phosphenoxide could be regenerated by removing the oxygen atom from the phosphenoxide. But it is not possible by catalytically activated hydrogen. Only silanes. In organophosphorus chemistry, silanes are used to remove the double-bonded oxygen atom from the phosphorus atom. But there are expensive silanes and cheaper silanes, and these are the most attractive silanes of the low price. But these polysilanes are of low reactivity, and German scientists elaborated a catalytic version, but we found that under, again, microwave irradiation, there was no need to apply this catalyst. Beller elaborated. Microwave irradiation made possible to eliminate the catalyst from the reaction mixture. Consequently, we applied a much greener method for the deoxygenation of phosphenoxides. Okay, so we arrived at a very important segment of this kind of lecture, and this is the so-called Hero reaction. The Hero reaction is a kind of coupling reaction. You know, the Suzuki reaction, Heck reaction, and so on, Sonogashira, and so on, where you have you can couple carbon atom with another carbon atom. In our case, the Hero reaction involves the coupling of phosphorus atom and the carbon atom. And Hero 40 years ago invented this kind of reaction, and he applied a palladium tetrakis catalyst. Palladium tetrakis catalyst that is not so good because it's sensitive and expensive. And we found that under microwave conditions, the excess of the reagent, dialkyl phosphide, I promised I will return to dialkyl phosphide, excess of the dialkyl phosphide may serve as the P ligand. How? Please fancy this tautomeric equilibrium. And here is the trivalent phosphorus ligand. So we elaborated this method, and also we extended the scope of this reaction to other model compounds. And the question was what the real catalyst is. Here is palladium acetate, here is the reagent, excess of the reagent, and eventually, without going into details, this palladium palladium P2 catalyst is the real active agent. We were the first to substantiate it. So the role of the reagent is to serve two P ligands, and the second role is to reduce palladium 2+ to palladium 0. And also we explored the full mechanism. We explored the ligation around the palladium, and just to be short, our excellent quantum chemist, Dr. Mucci, found that, of course, the bis ligation is the most favorable if you see the energy gain, integrated energy gain. So bis ligation, this ligation is too crowded, not speaking about the tetraligation. And also we studied some kind of model compounds. I cannot go into details, but the typical steps occurred. I mean, the oxidative addition, of course, change of ligands, rearrangement, and reductive elimination. These are the elemental steps of the coupling reactions, and we refined it and applied it to our case. It was also possible to apply, instead of palladium acetate, I didn't mention palladium acetate, nickel chloride. It is a good question. Which is better, to apply palladium or nickel? Well, nickel is cheaper but more toxic. So it depends on the situation. Nickel could also be applied, and again we substantiated the mechanism. And fancy, we here has had a great invention. The great invention was that not the generally believed nickel 0, nickel 2 process is responsible for the reaction, but the nickel 2+, nickel 4+ process. It was proved theoretically and also experimentally. And we had to fight with the referees to be able to publish these very well elaborated results. And eventually we could, of course, publish this in Pure and Applied Chemistry, and also recently in the Journal of Organic Chemistry, because we had to refute the finding of Chinese, very famous Chinese scientists. They assumed nickel 0, nickel 2 transition, but this was not true. They even added a reducing agent, totally in vain, reducing agent, and they reported 95% yields. That wasn't true. Okay, so chemistry is very adventurous. Also, let me just mention hydroxyphosphonates. Hydroxyphosphonates are the sisters of aminophosphonic derivatives, and these are again enzyme inhibitory and process enzyme inhibitory properties. And let me refer to the once upon a time applied trichlorphone as a plant protecting agent, insecticide, and we also elaborated a microwave method for the preparation of hydroxyphosphonates. And in the literature, it is a very well studied model, the synthesis of hydroxyphosphonate. And a lot of authors were very proud that they could elaborate the synthesis under solvent-free conditions. But they forgot that on the workup procedure, extraction, chromatography, recrystallization, they used a lot of solvents. So they claimed a green synthesis, but this was made wrong by the workup procedure. And we were, together with one of my PhD students, we elaborated the greenest synthesis of hydroxyphosphonates. We measured in the reactants, added some catalyst in a concentrated solution, and the hydroxyphosphonate precipitated in a clean form. And with filtration, we could obtain the clean hydroxyphosphonate. Okay, hydroxyphosphonates are very useful intermediates, and it was a surprising reaction that the hydroxy group could be replaced in a nucleophilic substitution reaction by an amine, because it is a so hindered carbon atom. But our quantum chemists observed an adjacent, a beneficial adjacent group effect that promoted the reaction. Again, hydroxyphosphonate could be phosphorylated to provide potentially bioactive compounds. And also, benzyl derivatives were prepared that were debenzylated by catalytically active hydrogenation. And also, we could rearrange the hydroxyphosphonate to the corresponding phosphates you see here. And this is the very famous reaction. We explored the mechanism, and here you can see the reactions of the hydroxyphosphonate. And also, we found a lot of species between the compounds we prepared that were of potentially biological activity. These were examined on sarcoma cells, and they had beneficial effect. And also alpha catophosphonates could be converted to alpha hydroxyphosphonates. And here we arrived at the last topic. I will be very short. The last topic is the preparation of this kind of hydroxy bisphosphonic acid derivatives. These kind of drugs are used in the medical treatment of osteoporosis that may be connected with menopause and other bone illnesses, bone cancer, unfortunately. Hungary is very famous about these products because these are manufactured and distributed by us. And here you can see the biochemistry, but I don't have time, unfortunately, to describe. Just I mentioned that there are osteoclasts and osteoblasts in our body. Osteoclasts are eating the how to say, the active agents, and osteoblasts are producing. There should be an equilibrium in our body, and if this equilibrium is shifted, then you will be healed, and then you will need to have treatment with these bisphosphonic derivatives. The most important derivatives are palmidronic acids, alendronic acid, ibandronate, bisandronate, and zonandronic acid. These are used. This is the last but one transparency. Together with my late colleague, and I suggest this lecture in memory of Alajos Grün, who helped me a lot in this project. We optimized this kind of synthesis. This was again a black box, a very black box. And we had to evaluate the mechanisms, and we have to develop optimized synthesis using phosphorus trichloride and phosphoric acid in different solvents. And even we patented our results here in the last, the lowest row, you can see the bottom. And also, and this I promised to finish my lecture, also we found that the application of ionic liquids is very, very beneficial. Even yields above 90% could be achieved applying some kind of ionic liquids. And it is very important because these chemicals, these drugs are of a high value, very high value, very expensive. So it does matter if you can prepare the agent in a 30% or in a 90% yield. And my final message is that I believe that ionic liquids will spread in the chemistry, in organic chemistry, not as solvents, not really as solvents, rather as catalysts and additives. Of course, there are several cases when ionic liquids will be used as solvents, for example, in the preparation of dodecyl benzene. Dodecyl benzene is the starting material of washing powders, for example. Okay, so dear Chairman, colleagues, ladies and gentlemen, here are my colleagues who took part in this research outlined. I have already newer colleagues as well, and I should like to thank for your kind attention.
Thank you. Thank you so much for your very informative and nice presentation. We learned many things regarding this phosphorus chemistry, and you have nicely explained some of the mechanism of these reactions and the role of microwave for this reaction. Thank you so much for your valuable time. I am requesting a few participants if you want to share at least one or two questions, because our next speaker, Professor Chakraborty, is also joined with us. So please, dear participants, if you want to ask Sir direct, if you want to ask some question, please raise your hand. One or two we can attend. If you have any questions, please raise your hand quickly. First of all, please raise your hand. Any participant wants to interact with Sir, or if you have any question, please raise your hand. Yes. Yes. Dr.
Okay. May I audible?
Yes.
Okay. Good afternoon.
Can you please start your video as well?
Yes, I'm trying.
Yes.
So,
you're audible. we can't hear you properly. Dr. Iqbal, we can't hear you properly. Your voice is not audible.
In preparation of dialkyl phosphonate, in step 1, you are using it. May I audible now? Professor Banerjee, may I audible now?
Can you please write in the
Hello?
chat box because your voice is not clear.
Okay.
Your voice is cracking, so you
Okay, due to
write.
internet is
Yeah.
not audible.
You please write in the chat box.
Okay, okay.
Any other participants? Any other participants? Any other participants from abroad? If you want to ask any question, or please raise your hand. So if there is no question, so thank you so much, sir, Professor Keklevi, because our next speaker, Professor Ashish Chakraborty sir, is waiting. So thank you so much, sir, for your valuable time, and thank you so much for your guidance throughout. Without your support, and it is not possible to conduct this kind of international conference. Thank you so much.
Thank you for the possibility.
Yeah, thank you so much, sir. Now I'm requesting Professor Ashish Chakraborty, can you please unmute yourself, and can you start your video as well? Yes, thank you so much, sir. Thank you so much. Now, can you hear me, sir?
Yeah, I can hear you. Do you see the screen?
Yes, sir. Yes, sir. So thank you so much, dear participants. Now we have our 10th scientific lecture. The topic of the title of this lecture is Application of Green Chemistry Principles in Pharmaceutical Research. So the speaker is, we all know, Professor Ashish Kumar Chakraborty, sir, is a famous scientist in India. Let me introduce sir. Professor Ashish Kumar Chakraborty obtained an MSc degree in 1977 in organics chemistry from University of Burdwan. Then he received PhD degree in synthetic organic chemistry from Cultivation of Science, Kolkata in 1985. And after postdoc, he joined Burdwan University. Then he joined Naipar Mohali, and he retired just 2019 August, and then he joined as a visiting professor in the Department of Chemistry, IIT Ropar. Very recently, he joined Cultivation of Science as a eminent professor, and he has published more than 179 research papers. His H index is more than 62. I-10 index is 156. He has 42 patents, and he has supervised more than 40 PhD scholars and 130 master's student theses. So he received many awards. He is a fellow of Royal Society, and he is a FNA also. So with this short introduction, I am again welcoming you, sir, in this international conference. Now you please share your slide, because we have made you the co-host. So now you can able to share your slide.
Thank you, Dr. Banerjee. I think the slide is visible at your end.
No, sir, I think.
I have shared it.
No, it is not, sir. Can you please try it once again? Yes, now it is, sir.
Okay, fine.
Yes, sir.
I think the full screen is coming now,
Yes,
right?
Yes, sir. Yes, sir. Thank you so much, sir. Now, please.
Thank you, Dr. Banerjee. As you see that the theme of the present conference is the recent trends in the green chemistry. And it is a very nice initiative under the leadership of Dr. Banerjee that Akal University is conducting the conference, and they have joined hand with the Indian Chemical Society. So I'm thankful to the President, Dr. G.D. Jadhav, and my good friend and younger colleague, Professor Chittaranjan Sinha, who is the secretary of the Indian Chemical Society, to promote the activity of the Indian Chemical Society to the furthest part of Punjab. So green chemistry is the focus in today's in this conference. So why green chemistry? So we know chemistry, particularly organic chemistry, is the another aspect of this conference. So organic chemistry, where the advantage of the organic chemistry, we can get a dividend. So only dividend we get in organic chemistry is in the area of drug development and drug discovery. So it has been unchallenged opinion that organic chemistry plays the critical role in the pharmaceutical industry, but they have mentioned that in the context of the new drug development, that it is better that at the same time that chemistry is coordinated with the other areas of drug metabolism and chemical toxicology. But there is no doubt about that one. The chemistry plays a central role in the drug discovery and development program. But the concern is that are we doing the chemistry in the right way? So to be more precise, that how to avoid the adverse effect of the chemical research on the environment. So, and this is demonstrated by the couple of remaining slides, is that what is the impact of the chemicals, means drugs and pharmaceuticals, on the environment. Chemical industry appears to be the most polluting industry. Like I have separated out oil and refinery, although it also come under the chemical industry. But if we specifically want to emphasize on the drugs and pharmaceuticals, then these three agenda, bulk chemicals, fine chemicals, and pharmaceuticals, are the major chemical industries. And the extent of the pollution by a chemical industry is measured by the E factors. And if we look at the E factors, we'll find out that it is alarming. That means the chemical industries are the major polluter of the environment. But at the same time, we can't live without doing the chemical exercise. So it is in this requirement that over 100 environmental laws have been formulated so that there will be comment on the control and treatment or abatement. And this has become, green chemistry has become a formal focus of the Environmental Protection Agency housed in United States of America in 1991. So it looks like that green chemistry directives, they are only regulating, they are asking not to do, but that is not the case. That the pollution and prevention law of 1990, which although objective is to prevent and eventually eliminate the need of treatment of the pollutant, but at the same time it encourages the development of new technologies and processes, chemical technology and processes, and it inspires chemists to devise new greener condition and looking for the new chemistry also. So it also promotes the new invention in such a way that newly invented procedure will be less, if not completely non-polluting, it should be relatively less polluting. So that is the reason green chemistry is considered to be synonymous of the sustainable development, means that meeting the economic, environmental, and social need of the present generation without compromising the ability of the future generation to their own needs. So what actually green chemistry does, it utilizes a set of principles to reduce or eliminate the use or generation of the hazardous substances in its either design, manufacture, and application of the various chemical products. So there is a set of principles which will give you some kind of roadmap that it is possible for you to, if not totally eliminate, minimize the pollution out of the environmental exercise, chemical exercises. So it is also a practical approach towards this direction, and that is the reason in the vision of American Chemical Society, the green chemistry is improving people's lives through the transforming power of chemistry. So in the routine chemistry exercises, how to address it? Now, these parameters which are called green matrices, and what has been highlighted in the green light shade. So those are the cases it is possible to address in the research laboratory. It is not like that green chemistry is always the component of the industrial exercise. That green shaded exercises or the matrices can be very well addressed in the laboratory even. So it is in this context, I thought that why not to sensitize people that green chemistry practices in pharmaceutical research, and their sensitization has been already there. So where is the scope of the pharmaceutical research? That this is considered to be a typical drug discovery funnel. It says that if you put on the top of the funnel closely about 10,000 compounds and let it go through the various level of the assessment for the purpose of the drug, and perhaps one molecule might come out for that. So looks like that Baki remaining 9,999 molecules which have been synthesized, they are synthetic routes. This molecule ultimately will go to the for the bulk production. But how about the remaining 9,999 molecules? And these are not the same molecule. They are the diverse classes of molecule. So the efforts that has been done to make those molecules and those chemistries also need to be addressed appropriately in the context of the green chemistry. So the green chemistry has a scope in the discovery phase. And once the molecule comes out of a potential drug candidate, then it goes to the industry and the bulk production, and where it is going to be obvious application of the green chemistry principle. So though this is with reference to industrial exercise, but here is a case where in this out of 10,000 making the molecules, there is a scope in the discovery chemistry to address the green chemistry. So this is in general activity of the drug discovery and development. The drug discovery generally in the domain of the medicinal chemistry, basically chemical synthesis, and new drugs, which is called a discovery phase or new drug discovery. There is enough need and the scope of the chemist to address the green chemistry principle. And in the development stages also, which is under the chemist domain, is the new process development, particularly chemical processes, but technology is the enzymatic processes. So here, so what we see that not only in the industry level, which is normally the process development, in the laboratory level also, which is called discovery chemistry, there is enough scope and requirement also to address to the green chemistry principle. So under this backdrop, I thought that let me highlight you how it can be addressed. So it is not like that the thought process has been generated very abruptly for that. There has been a discussion in this regard, and this article has nicely summarized that how green chemistry tools are going to influence the medicinal chemistry and other kind of chemistry research based organizations. That means it is both addressing the discovery chemistry as well as the process chemistry. Generally in the discovery chemistry, the medicinal chemistry, I have been practicing medicinal chemistry for more than last 25 years. So it looks like that, the perception is like that in the traditional medicinal chemistry school, that medicinal chemists tend to do everything other than the chemistry. And this has been well recognized over the years throughout the globe, and people have been worried about that. So that is the reason to sensitize this kind of mindset. This article has appeared in the Journal of Medicinal Chemistry. So what it tells that generally medicinal chemistry, they feel that everything has been done by our neighboring university having a organic chemistry department, and we have nothing to do. Whatever the method they are developing, we are going to adapt it and do it like that. So it is just to sensitize this mindset that it says that there is a necessity to further synthetic research that are currently underrepresented and are in clear need of robust, reliable, and widely applicable methodology. Even there is a need to already tried and tested and maybe widely employed methodologies, particularly chemistries, where there also is a clear deficiencies in areas such as atomic economy and safety. So it is not like that everything has been done, all the chemistry has been done. Whatever the chemistry has been done is not enough in today's context of the cleanliness of the environment. So these methodologies need to be improved in the context of the safety, cost effectiveness, scalability, and most importantly, overall greenness of the environment. So how to do it? Now, the suggestion is like that. There is necessity to have an intense discussion, crosstalk between the synthetic and medicinal chemistry. As a matter of fact, there is a necessity to crosstalk between synthetic organic chemistry and medicinal chemistry also across the industry and academia, so that you can have an enhanced impact of the new chemistries, new methodologies which are coming up for the future drug discovery program. So clear-cut recommendation has come. This another article to sensitize particularly the discovery chemistry people, because that is the chemistry generally undermined in terms of the greenness, that in the synthetic strategy, why not to adopt the CH activation? Over the last 20 years or so, a lot of new chemistry has been done under the name of CH activation. Why don't we adopt this? Because there is a lot of proclaimed advantage in this doing. And aqueous chemistry having over the probably last 30 years or so has been very much impact on the organic chemistry, but looks like that these are not being properly reflected in the discovery phase. It is for this purpose, this article has appeared in the Journal of Medicinal Chemistry. So keeping those things in mind, we try to adapt in even our purpose of making a new chemical entities for the purpose of focused biological evolution for the different disease area. Wherever there is a feasible and there is a logical reason behind that, use alternate reaction media. We know there are 3 or 4 types of popular organic reaction media, like reaction media for the organic reaction, water, ionic liquids, fluoride solvent. Now deep electric solvent is coming also. So I am not talking about ionic liquid today or maybe fluoride solvents. I'll take some example of the water, how it is giving a sustainable way for the drug discovery and development. And under the catalytic processes, logically we focused on solid supported protic acids. We will not talk about there. So we developed a lot of very efficient catalysts, and many people in India and abroad in the reputed laboratories are using our catalyst and doing various kinds of transformation. But today I'll focus about these 2 aspects, that CH activation through a transition catalyst reaction, and of course taking advantage of the nanocatalysis also, because that gives a distinct advantage in the catalytic processes. So sustainability using aqueous chemistry. So there has been a report, maybe as early as 1980s, that water can be used as a reaction media to carry out various organic reactions. And there has been a report that use of water do have a distinct example that it can accelerate the rate of the reaction. There has been reports occasionally that it can change the selectivity also. And people have used aqueous mediated organic synthesis, if not for the target molecule, at least the important intermediate. And how exactly water gives the beneficial role, that has been also projected, that primarily it is an hydrophobic effect, but it is possible to take advantage of the hydrogen bonding effect, provided you can structurally manipulate the reacting partner. But what we realized, that all those philosophies of the proposal are with reference to a particular set of organic reactions, particularly Diels-Alder reaction. So we wanted to extend the beneficial role of the water, understanding the beneficial role of water as a generalized reaction media. And we had a query that what could be the molecular level role of water, so that they can interact with the substrate and can have a distinct advantage in promoting a organic reaction beyond the scope of the Diels-Alder chemistry. And their hydrophobic interaction is the major reason behind that. And since we work in a pharmaceutical institute, so naturally for various reasons, we have to manipulate the nitrogen functionality for the peptide synthesis. Even nitrogen containing amines are starting material or the intermediate. But during their use as a starting material, we have to manipulate the nitrogen functionality so that you can carry out a reaction at other side, which is called masking the nitrogen group. And very popularly it is done by the Bock protection. The most popular catalyst has been 4-dimethylaminopiridine, but that is a banned entity, is extremely mutagen and a lot of toxic material also. So we tried to think about an alternate in this regard. We found out that Bock formation reaction can be very easily promoted in aqueous media. You don't need any organic or inorganic catalyst. And we propose that the only way we can interpret the molecular level role of the water is that because of the hydrogen bonding ability, it is going to make hydrogen bond with the carbonyl group of the Bock anhydride, so that it is activating the electrophile. And in the next stage, through the transition state 2, the same water molecule through the oxygen atom can undergo hydrogen bond formation with the amine nitrogen, so that it makes the transition state 2, and then it can activate the nucleophile also, and ultimately the reaction will go. So very clean reaction. You don't have to monitor the reaction by TLC, because as long as the reaction will go, you will find out the effervescence of carbon dioxide. When it is complete, the reaction will seize out, and if the compound is a solid, it will precipitate out. If it is an oily, either it will settle down or it will float. And for solid material, very easy to purify. For the liquid material, maybe you have to make it water-free. So we attributed the role of water here, that amphiphilic means electrophile, nucleophile, dual activation through hydrogen bond formation. So you know that one shallow doesn't make it a summer. So is it restricted to a particular type of reaction? So we wanted to find out that for versatility of this proposal for promoting another reaction, and due to again our synthetic need, we had to get this kind of compound, and structurally they can be considered to be a thiamical adder. So there have been a lot of catalysts reported for that. We also developed a half a dozen of transition metal based and the solid supported catalysts in this purpose. But our primary objective to take this final product to a further structural manipulation is that they are going to be subjected to the enzymatic analysis, enzymatic inhibition for getting their desired biological activity. And enzymes are very much sensitive to trace amount of the metallic species, and sulfur being a very good coordinating agent. So any metal we use in the reaction, it will be very difficult to make it completely metal-free. So we had a need to have a completely metal-free thiamical addition reaction to start getting our starting material, and so that we can progress further. So we thought that can we put into use that hydrogen bonding efficiency of the water molecule, and the same way it can be promoted. So we propose that this is the first stage activation, electrophilic activation to hydrogen bond, and this is the second stage. Again, similarly, sulfur H is undergoes hydrogen bond formation reaction, activating the nucleophile, and the reaction should proceed. It works very well, although there is a limitation also. But what we derived from out of the early studies is that looks like that in majority of the cases, the role of water can be considered as a ambiphilic, means electrophile nucleophile dual activation by cooperative hydrogen bond formation. And this happens to be a early direction in understanding the molecular level role of the water. After these two papers came out, so we found out in the Science a paper came out. So what they did a gas phase reaction of an hydroxyl radical with an aldehyde molecule, and in being promoted by a single water molecule, and they found out that no, it is a single water molecule promote this reaction. And the kind of proposal we have projected prior to this publication, the same proposal they have adapted. Only thing is that they have demonstrated by calculating the energy to the very high-end calculation. So point is that the same ambiphilic dual activation has been utilized. So this is just to substantiate our proposal. Then we found out that the same proposal has found out a more than 50 years old fallacy in the marine chemistry, that in the marine natural product, we get a polyether, cyclic polyether kind of molecules, right? They are all 6-member, means they have a THP skeleton. So these are various kinds of toxins, and to mimic the smaller structure of the toxin, so people try to do a lot of efforts in the synthetically to make a smaller molecule to find what is the smallest structure can mimic the activity. So any activity they try to do in the laboratory, the classical organic reactions, they end up with either getting a THF product, means 5-member cyclation product, or a mixture of THP and THF. But when the reaction is performed in the water, it is only in water, and so then they give a proposal that why in marine this thing happened, because it is a 2 water molecule, they undergo similar kind of interaction with the epoxide molecule, and which has been proposed by us. So we are very much happy that whatever the earliest proposal we have given, that has been put into use to explain various kinds of aqueous mediated reaction. And it was really proved to be true that ours was really a very good indication. Organic letters, what they did after 25 years of completion of their publication, 20 years probably. So they made a virtual platinum anniversary collector's edition. So what they did, all the first 20 years, they have picked up one publication from the organic letter. And that was a select expertise was there, and they made the compiled issue. And we are very much happy to observe that this initially Bock formation reaction of water media. This has been in 2005 issue. This is the 2006 year they have picked up this one, and this is the only article representing contribution from India in this collection of the first 20 years of publication in organic letters, which tells that whatever the proposal we have given, what is the impact of the proposal in understanding aqueous chemistry. So by this time, we know that we can manipulate the use of water and to make various kinds of molecule and put into the use by taking the direction of the integrating green chemistry to the discovery chemistry. So these are the various kinds of activities we can do, we have done so far. But today I will demonstrate you one example of formation of a PDO-free inhibitors for the purpose of a therapeutic agent for treating asthma or COPD. And this is the discovery chemistry. And in the development chemistry, in particularly process chemistry, I'll take up two examples, which is a completely all water-assisted reaction. The last one is completely all water synthesis for the two drug molecules. So let me tell you that how we can adapt the green chemistry practice and principle in the discovery medicinal chemistry for the purpose of generating new anti-inflammatory scaffold. Inflammation generally supposed to be the normal defense mechanism of any living system to protect it from any invasion from the outside agency. But if the inflammation become uncontrolled, then it becomes a major health problem. And one such inflammatory disorder, maybe two such disorder, one is rheumatoid arthritis or chronic asthma, and second is the phosphodiesterase activity, particularly the COPD. So the COX-1, this is the rheumatoid arthritis, either selectively COX-2 inhibition for that. And for the other activity is going to be the asthma and COPD, for which the target is PDE4. So I'm going to talk about the PDE4 today. In the context of today's health catastrophe, particularly COVID-19, it is also a completely inflammatory disorder. So naturally, people try and happens to be working in the same organs where PD inhibitors also supposed to work, or maybe the asthma pathogenesis takes place, particularly lungs. So what has been found out that PD inhibitors, they are found to be useful for the treatment of the pathogenesis. In the clinical cases, they found out that symptom can be either completely or partially tackled with the COVID-19 situation, like thrombosis, inflammation, and fibrosis. And a few selective PD inhibitors or pan-selective inhibitors are under current study to see that whether they can be dedicated treatment for the PDE4. Either PDE4 inhibitors alone or in combination with other drugs could be beneficial for the treatment of the COVID-19. More importantly, that it will have an economic impact, particularly it can slow down. Yes, Professor Dandia. Yes. Fine. My lecture is in progress. So it can at least slow down, if not totally control the disease, slow down the progression towards the most severe stages. But that was not in the picture when we started for that. But in today's scenario, looks like that we can have a more advantageous in finding a new PDE4 inhibitors. So we are looking for a PDE4 inhibitors, particularly PDE4 selectivity. The reason is that the first PD inhibitors which were projected in the early stage is the first generation PD inhibitors, the Rolipram. But PDE has a 9 isoform. It is a specific PDE4B2 isoform should be inhibited. Other isoform has different kind of activity. One more PD inhibition which provides a therapeutic is a PDE5, which is called sildenafil, is a erectile dysfunction for that. But it is called a panacea of pathogenesis. But PDE4 B2 is the target, but Rolipram actually is a non-selective inhibitor. So that's why a lot of side effects are associated with Rolipram, particularly nausea and vomiting. So there has been a lot of efforts to make a new PDE4 inhibitors. And in this race, two molecules, piclamilast and roflumilast, they went to the advanced clinical trial. But ultimately, piclamilast lost the race, and the roflumilast finally was approved. And in 2010, it was approved as a Dalires as a trade name for the treatment of the COPD. But as I told you, that it is a panacea of the pathogenesis. Other PDE4 inhibitors, apremilast, they have been approved by FDA in March 2014 for some other kind of, not for the COPD or asthma, for other kind of inflammatory disorder, particularly psoriasis and psoriatic arthritis and various other kinds of diseases. So it looks like that this provides you a opportunity to extend its therapeutic applicability for the other disease pattern also, which might be talked about as a drug repurposing or repositioning the drugs, the same drug molecule. So while looking for a more selective PDE4 inhibitors, because when we started this work at the time, roflumilast is yet to be approved, but we know that it is an active molecule. So we found out that any modification we do in the upper part of the molecule, the entire molecule can be the prototype molecule, rollicram can be divided into two parts, northern part or the moiety A, and the southern part or the moiety B. So it was found out that generally the northern part is a conserved region. So only thing is that you have a catechol moiety only, there might be different alkyl group attached to the oxygen of the catechol moiety. So only scope you have to really structural modification for the purpose of making a different molecule is to make a modification of the lower member ring. So we did a quick computational or what we call that virtual screening, and what is going to be the bioisosteric heterocyclic moiety which can feed or sit comfortably selective in a PDE4 B2 active site. And we found out that benzothazole is going to be, so B is the A is a rollicram and B is the, so they very effectively sit in the active site pocket of the PDE4 enzyme. So we found out fine. So this is going to, we can have a replacement in the lower part of the molecule as a benzothazole ring system. So now this is the medicinal chemist job, it's a thinking process only. Now comes the chemist job, you have to make the molecule. So there are various kinds of ways to make the benzothazole moiety, and in the context of the green scenario chemistry, that none of them are going to qualify. So we thought that can we put into use the dual active? So in this regard also, the previous Dr. Kaglivi very nicely demonstrated the application of the microwave chemistry for taking the phosphorus chemistry. So microwave chemistry has been in the picture since maybe early 1980s. And we have been also trying to make use of the microwave chemistry. We found out that why not to do the same condensation reaction, because classically the condensation reaction is done by using a stoichiometric amount or PPA, polyphosphoric acid as a solvent, and heating at 200 degrees centigrade or so. So a lot of phosphoric acid has been liberated, so that is not going to be a very clean procedure. So we found out that yes, this cyclodehydration takes place under microwave. It works, but there are two disadvantages. There is still a apprehension regarding the scalability of the microwave process, but maybe microwave in conjunction with the flow chemistry one day might be the technology of the tomorrow, but it is yet to come to that extent. Second disadvantage is that depending upon the individual carboxylic acid physical properties, that sometimes tends to undergo decarboxylation reaction. So we want to have a milder way to condense this reaction, and herein we thought that why not, by this time our water chemistry we became interested. So we put to use that water, the dual activation role, because this is also a combination of electrophile nucleophile partner, and the reaction works very well. Heating at 110 degrees centigrade, reaction works. Here also, that not much effort has to be done to purify the compound. If the compounds are solid, they precipitate out, and simply one have to decant and maybe make it dry. Only you might require to make it water-free in case it is a oil or maybe a completely liquid in nature. So it works. So we started testing the molecule, but then we tried to find out that is there any distinct advantage in using water. To demonstrate that, what we did, we performed the reaction in water as well as in all the classical solvent, and as we find out that the rate of the reaction determined by the Kigel's GCMS and not the physical chemist way to determine the rate of the reaction. The way organic chemists do that, within 10 minutes, both the starting metal completely consumed when the reaction is in water. In all other solvent, the reaction rate is a little bit longer. Then this is in terms of the reaction kinetics. And then there is another issue also here, the selectivity. The reaction actually proceeds via the initial formation of the dihydro product or benzothazolene, and it has to liberate we call an oxidation or dehydrogenation reaction to the final product. So this is the more significant issue of the problem, so that you are not going to get a mixture of the product. And we found out that when the reaction is performed in water, not only in 10 minutes the reaction is complete, you have a completely clean conversion to the desired product. So all other solvent and etc. you are getting, depending upon the solvent, a significant amount of the undesired product. So very happy. We started making the molecule and parallelly testing them with the enzyme assay. But then by this time, we started becoming a little bit more focused in addressing the green chemistry as much as possible in toto. And we realized that the reaction need to be performed under heating at 110 degrees centigrade. So we found out that looks like that the second agenda of the green chemistry index is not going to be fulfilled here because consumption of energy is there. So for that, can the reaction be performed at a room temperature? And the way generally organic chemists believe that, because since these are a reaction with an organic molecule in aqueous media, because they are insoluble, so that is the reason you have to heat it. And to avoid that criteria, people try to use certain addendum which are known as a solubility enhancer of the organic compounds in a aqueous media. Those are called surfactant. So in this context only, initially, we tried to screen various, use various surfactant to see that which surfactant is going to do the job so that the reaction can be performed at room temperature. So all the surfactants are divided into three categories: neutral, like the first three are neutral. Then these are cationic surfactant, and then there are these are also neutral surfactant, and these three, and 9 to 11, they are anionic surfactant. So we found out that these three anionic surfactants are working best. So now, since the major issue is that are we getting a clean conversion to the desired product 3A, or there is going to be accumulation of the undesired product CB. So we find out, except this anionic surfactant, all the other surfactants, there is a significant amount of the accumulation of the undesired product. So, and among these three anionic surfactant, ACE-DOS, sodium dioptyl sulfosuccinate, henceforth, it will be treated, designated as an ACE-DOS. This happens to be the most effective catalyst. So since our presumption was that they are going to be act as a solubility enhancer, so we want to see that is it the case. Then we found out that actually when we are performing the water using ACE-DOS, the reaction is not exactly clear-cut. It is homogeneous, but it is not a transparent reaction mixture. It is to some extent colloidal. More importantly, when ACE-DOS is used, but in place of water, we are taking organic solvent, then it became a completely clear reaction mixture. That means solubility is actually completely is there, but we do not get a very good conversion to the desired product. See, we almost get 1:1 formation of C and D. So it is not the solubility which is major concern over here. So then we wanted to know that what might be these are the different other organic solvents. So it is not the solubility is the major issue advantage you are getting by using ACE-DOS. So to prove that, what we did a few critical control reaction. That first three entries of these tables are the reaction in water, but in the absence of ACE-DOS or actually any other surfactant. And we did find out that the reaction works very well. That means overall condensation is working. You do not need any catalyst actually to make this electrophile cyclocondensation reaction. But the major product is the 3B. So you are not getting the final product. Same aqueous condition, but if we are adding ACE-DOS, then the reaction become a complete conversion. After 60 minutes, you get a complete formation of the 3A. So then probably what is this now? 3B can be converted to 3A. We call it a dehydrogenation reaction or oxidation reaction. But who is going to help you to dehydrogenate? Somebody has to capture the hydrogen. So we thought that it is going to be aerial oxygen, which is going to capture the hydrogen to be converted to the water molecule. And that is the reason the reaction is taking place. So we thought if that be the case, why not we pass on oxygen gas to the reaction mixture and see whether we do really get any advantage in terms of the making the reaction a little bit faster. So the next two entries, D, footnote D. So we found out that if we pass the entries are performing the reactions, but passing the oxygen gas, and we see that condensation reaction to form the product signal of ACE-DOS. So it looks like that ACE-DOS is required. Are you being able to see my slide?
Yes, sir.
No, because sometimes I'm getting that your internet is not stable. I thought that whether it has been disconnected or not. In case it gets disconnected, intimate me, Dr. Banerjee, right? So then what we do, that we perform the last 3 entries are performed in aqueous media in the presence of S-DOS, but we have degassed the water which we have taken, and on the top of that we bubble nitrogen through the reaction mixer, so that there is no trace amount of the oxygen. And we did find out that yes, cyclocondensation takes place, but you get a 1:1 mixture of C and Cd. So this tells that a role of S-DOS is not to solubilize the starting material. The role of S-DOS and water both is required, and also oxygen is required, because if you have a nitrogen atmosphere and degassing also does not require. So what you need to get a clear-cut conversion to the desired molecule, you need water as a reaction media. You need the presence of oxygen. Only thing is that it can be aerial oxygen, open vessel reaction, and most importantly, you need S-DOS. So if that be the case, then the capability of the different surfactant certainly should be associated with their ability to capture oxygen and somehow transfer to the reaction media. And we did it through an oxygraph study available in our biology department. We do not have in the chemistry, actually the biologists do it very routinely. We call it oxygraph. And we did find out that all other catalysts, which are inferior catalysts, they have a poor ability to capture oxygen. And the 3 anionic surfactant SDC, SDS, and S-DOS, and S-DOS is the most effective agent to capture or has the highest oxygen uptake capability. Then we found out there is a very good correlation between the micellar concentration and the amount of oxygen. It looks like that 5 or 6 to 10 mole % is the optimum concentration you need in S-DOS. So what is happening over there now? If we take water, so without the requirement of any catalytic assistance, we get the cyclocondensation. But here is the case: we need the presence of water, presence of oxygen in the form of open air, and you need the surfactant. So that means you need water, you need oxygen, you need a surfactant, and these are the 2 effective surfactants, S-DOS and SDS. So what exactly might be their role? So that means somehow these 3 have a coordination, and only clean way to represent their coordination activity will be that this is actually S-DOS, this is the sodium like anion molecule, and this is the role of the water molecule, and this is how oxygen can be attached. So through this supramolecular assembly or non-covalent assembly, A is the active species for the S-DOS and B is for the SDS. So these are the effective species through which oxygen is being taken up from the air, and then in the water molecule it is being delivered, and that is the reason that the conversion of the thiazolene 3A to 3B is taking place. So then we have to prove it that this is really the happening. So how do you prove it, their presence? Now these are the supramolecular assemblies, non-covalent attack. We can do the classical way for the characterization, like isolate it and do the NMR and etc. But by this time, mass spectrometry has been the only reliable tool to identify the presence of the non-covalent attack. Generally, the biological molecule people have done. We have extended it to the small molecule. We were the earliest people to represent that mass spectrometry can be used for the small molecule for identifying the non-covalent attack. And we did find out that we can identify in the reaction mixture. Repeatedly, we have done it, and this is the actual species for that. And through repeated MS studies, we were convinced that this is going to be the active species. This is in case of SDS, and the same thing is S-DOS. Also, we have done a HRMS studies also, and so that there is no ambiguity in this regard. So this is the corresponding active species when S-DOS is the catalyst. So if that be the case, then is it, since these are the active species, reactive intermediates, so as per the principle of the physical organic chemistry, as the reaction progresses, there is supposed to be a steep increase of their concentration, should reach a plateau and slowly try to come down. So ESI provides you a scope, because you can do a quantitative mass spectrometric measurement, and ion current measurement of the respective ion peak will tell you that what is the concentration. So these are the area of the corresponding peak corresponding to the ion current. This is the corresponding log. So what we see that that the maximum ion current will get it. And there's a very good correlation between the micellar concentration, but that is not important. What is more important is that, so this is a very good correlation between the micellar concentration. So it looks like that it become a plateau, the ion current, when it become 5 to 6 mole, 5 to 10 mole%, there is not much increase after that. Most importantly, there is a very good correlation between the oxygen uptake and the ion current, so that it can convince that this is the way it is taking place. So we had a room temperature condition, and we did synthesize an appreciable number of molecules, and they were subjected to PDE4 inhibition. Out of that, this molecule appears to be a promising one. So my industry colleagues who has listened to me earlier, they have told that if you are getting a PDE4 inhibitor into 100 micromolar level activity, so you should be very much conscious about that one, because it might lead it to somewhere. So, and in this context, this is a nanomolar level activity. But what we found out that if we compare this activity with the roflumilast, it is not as active. So naturally, and this is also not probably the optimized in the structures. We thought that there is no much scope to change the left-hand side of the molecules. So we didn't try. I am not sure about that one yet. I have to check that one, whether it works or not. That some of the side chain, which is cyclophosphamide, the problem is that boronic acid requires 20-step synthesis. That we have done for our industry project. We didn't want to mingle up for that. So probably this is the best combination of the ether side chain. Not much we can change it. We have done a lot of other things, right? So, but there is a scope of modification of this ring. So how do we do it, right? So there is a speedy conversion of the lead to lead optimization. And we know by this time that late stage functionalization, a CH activation has been proposed, and it has been projected by give me a minute, probably it got stuck with some reason. So we again took into the consider each activation is the one way. But at the same time, there has been a concern in the domain of the medicinal chemistry. This is probably 2016 JMed Chem paper. That last 20 years or so, you have developed so much novel chemistry, CH activation, meta selectivity, etc., etc., etc. But where have all the new reactions gone? So looks like that they are not being reflected for the purpose actually you develop in.
Sorry, dear participants, I think there is some technical issue. I think Professor Chakraborty has lost the connection. Maybe we will join within a few seconds. Yeah, Professor Ansudanya, madam, please wait at least. I think Professor Chakraborty has disconnected. So somehow, because maybe some poor connection.
Yeah. So if you like, we can start.
No, I think we at least wait for the for at least up to 4. Let's see.
Okay, that will be nice. Okay.
maybe due to bad weather today at Kolkata, there's a heavy rainfall, so that may be the reason there is a bad uh, network. Dear participants, I have just now talked with Professor Chakraborty over phone. He is trying his best. He will return back within a few seconds. So please wait because we need to give him a thanks. So after that we can start. Dear participant, Professor Dandia, can you please unmute and start your video as well? So there is some technical problem in with Professor Rossi Chakraborty's system. He lost the connection, so that's why he requested Professor Dandia to start her lecture again. After her lecture, Professor Rossi Chakraborty sir will conclude his lecture. In the meantime, he will arrange some intervention. So now we will start our this is our 11th lecture. So we are very much thankful, madam, for your continued support, and without your support it was not possible for me to organize this type of mega event. Or so thank you so much, ma'am, for your support and guidance. So now this is the 11th scientific lecture. The title of the talk is Moving Towards Sustainable Future of Chemistry on the Wheels of Green Chemistry Technologies. Let me introduce Professor Dandia. Professor Dandia is presently Emeritus Scientist, UGC BSR Faculty Fellow. She is the member of editorial board of renowned journals, current research in green and sustainable chemistry published by Elsevier. She received two prestigious scientific awards from two prestigious Scientific Society of India, MRSI and CRSI. Professor Dandia is a fellow of Royal Society of Chemistry. She is a member of American Chemical Society, IUPAC, and International Green Chemistry Network. She has already published more than 200 research articles, and all are in internationally reputed, highly impacted journals. Her H index is around 36. I-10 index is total impact factor is 254. Total citation more than 4,000. So she has supervised more than 50 PhD research scholar and several MSc projects. So with this short introduction, madam, I again welcome you in this international conference, and once again thank you so much as you are attending almost all the lectures. Thank you so much, ma'am. And now you please share your screen, and then please start your lecture. Thank you, ma'am.
Thank you so much, Dr. Baboon, for giving nice words of introduction. And can you see my slides?
No, ma'am. Please share. I think it is not shared.
Let me check first again. Sharing आपके इसमें आ नहीं रहा है.
Yes, we have made you co-host, ma'am, already.
Pardon?
We have already made you co-host. Now you can easily share.
But sharing option, it was previously coming. I don't know where has gone this. Just let me check first.
Center bottom share screen.
Yeah, it was there.
You just touch the cursor. It is just center at the center.
Yeah. Just wait. Now is it shared?
Yes, ma'am. Please make it full screen and you please proceed. Thank you, ma'am. Madam, please make it full screen.
Yeah, I'm trying, but what is happening in this?
please make it maximize, ma'am, and then you can find.
Yeah, I'm trying. Always I do this, but I don't know what is happening today.
Ma'am, please make it maximize.
I'm trying, but I don't. Just wait little bit. I'm not sure what happened to this.
No, ma'am, I'm trying to help you. And so try, please, first of all, you please maximize the file.
Okay, let me check.
Top right side. Top right side. Please maximize the file.
This file is not opening now. Screen sharing is paused. It is mentioning. What happened?
Yeah, please make it maximize, ma'am. Not minimize, maximize. Upper. Yeah, yeah, maximize, please do.
स्लाइड शो मैम स्लाइड शो ऑप्शन आ रहा है
नहीं वो मैं कर रही हूँ
Slide show.
हाँ that I am doing
Set up slide show.
हाँ जी yes
then what's the problem again
from beginning मैम कर इसको कैंसिल कर
let me start again मैं शुरू से करती हूँ वापस
Okay, okay, ma'am.
It was working well previously. I don't know what happened.
shift F5 shortcut
It's not going. I don't know what is happening. Maximize.
It is not shared right now. You please share the file.
But when I try to maximize it is not maximizing. So,
You please share your file once again. Ma'am, your video is off, ma'am.
no, but this problem, it is not going.
Ma'am, press Shift and then F5 at a time.
That is, I am trying. I don't know what is the problem in this now.
मैम जो नीचे दिख रहा है ना आपको क्लिक टू ऐड नोट्स के ऊपर जो बार है उसको प्लीज राइट साइड करिए स्क्रॉल नहीं हाँ हाँ इसको राइट साइड करिए प्लीज हाँ छोड़ दिए हाँ जी तो इस पर नीचे एक सेकंड
पर इस पे ये मैक्सिमाइज नहीं हो रहा है ना प्रॉब्लम इज दैट
यहाँ पे क्लिक कर जो मिनिमाइज के साथ में
मिनिमाइज के साथ जो ऊपर है मैक्सिमाइज
हाँ जी मैक्सिमाइज
आ नहीं रहा है वो साइन नहीं आ रहा है इसमें
मैम जो मिनिमम मिनिमाइज देन मैक्सिमाइज देन क्रॉस देन क्लिक ऑन द मैक्सिमाइज साइन
साइन नहीं आ रहा दैट इज अ बिग प्रॉब्लम
मैम साइन नहीं क्रॉस के बाद जो लेफ्ट साइड में है उसको प्लीज क्लिक ऑन दैट
वो
मैम ये फ्रॉम बिगिनिंग कर दीजिए वहां पे क्लिक कर दीजिए ऊपर साइड पे इधर साइड पे हाँ जी यहाँ पे क्लिक कर दीजिए Done. ठीक है मैम.
It's okay?
Yeah, ma'am. Thank you so much.
Okay, sorry, it was working well. I tried already to, anyway. So it is visible there.
Yes, ma'am. You please.
And I am audible also?
Yes, ma'am. Yes.
Yeah. So first of all, I would like to, okay. Yeah, I would like to thank Dr. Bugun for organizing this conference on such a mega scale. And I must congratulate you that you have organized this conference. And also I'm thankful to Indian Chemical Society, whose collaboration have inspired you to arrange this type of activity. And I'm thankful to President of Indian Chemical Society, Professor G.D. Yadav, and the Secretary, Professor Sinha, as I want to inform you that I have been the Vice President of this society and also the council member of this society 2 times and contributed a lot to this. Is there any problem there? Hello?
No, ma'am.
Okay, then something is there. Anyway, if it is visible. So today I am going to discuss the some problem is coming on this side. I don't know what is it. Anyway. So as this is 11th lecture on this series, the role of the green chemistry. Actually, everybody has talked about the green chemistry and what is the importance of chemistry. Why do we need the chemistry? Because it is needed to improve the quality and the quantity of the life. And the chemistry has improved our quality and quantity by providing large number of chemicals and materials, value-added materials, which have been used as photographic sensitizers, life-saving drugs, optoelectronics, agrochemicals, etc., etc., etc. So the organic chemistry basically contribute more to provide these type of chemicals. And whatever chemicals we are using are either obtained from the natural sources or they have to be produced industrially. And when we produce them industrially on the large scale, then they require the huge amount of the hazardous chemicals, volatile solvents, corrosive mineral acids, producing the pollution of water, soil, and air. So there is a need to develop the alternative methodology to provide the sustainability. And actually, this chemistry, that is, we have to pay the cost of this industrialization. Although the large number of accidents and disasters have been occurred due to the excessive industrialization. On the other hand, the industrialization has also caused the environmental issues like the acid rain, smoke, global warming, ozone depletion, etc. So there is a necessity to develop the solution for this. And the solution for this is the green chemistry. Actually, the 12 principles of the green chemistry were laid down by Paul Anastas and John Warner in 1991. But the term initially was given by the Ronald Breslow. Actually, we chemists, we are responsible for producing the environmental pollution. So we are responsible to find out the solution for this. And you can see that there is no green geology or no green astronomy, because only this adjective is used before the chemistry. And the people used to laugh at that time. How can be the chemistry green? Why can't it be of other color? But actually the green is related to the solution of the environmental pollution. It is related to the nature and plants-based things. So chemistry is the only science that introduces new substances into the world. So we have to see, we are responsible for their impact in the world. So naturally, we chemists, we have to find out the solution for this. It is our responsibility, and naturally the term was introduced, and to find out the solution, to find out the development for the sustainability, as we already, other scientists have told you about the sustainability. It is a meeting the needs of the present generation without compromising the need of future generation. So to develop the sustainable process, these are the various goals which we can use of catalysis, use of least waste production, process must be efficient, energy saving, without using the solvent, renewability of the conditions and health and safety, etc. So we can see that the green chemistry means without polluting the environment. While once the pollution is caused, then it is not useful too much. So green chemistry is not a solution to all environmental problems, but it is the most fundamental approach to preventing the pollution. Instead of producing the pollution and finding out the solution, we should try to make the synthetic processes in that manner that it is not causing the pollution to the environment. So 12 principles of the green chemistry were laid down by the father of green chemistry, Paul Anastas and John Warner. Professor R.K. Sharma has already mentioned about it. So these 12 principles, again, I'm not going into the details of this because it has already been included in the syllabus or the curriculum of MSc or the BSc classes of various university and colleges. But to develop the green chemical processes, we should try to incorporate as maximum number of the principles. Although it is very difficult to develop any process that is 100% green, but we should try to make the process simpler in that manner that it should be greener. So the dream of the green chemistry which involve the process must be atom efficient with the minimum number of the steps, simple, generating no or the little waste. It should be eco-friendly, safe for the operation, starting with the cheap materials or the renewable sources, with giving the maximum yield. So what we do in our laboratory, actually I have started working in the field of green chemistry and especially in the field of microwave enhanced chemistry in 1991, just in the beginning when it was started in the India. And from that, I think almost 3 decades we have completed for working in this field. And we have worked extensively in this field. So the objective of the synthesis of heterocycles, our basic interest is on the development of value-added heterocycles. Not only the pharmaceutical industry, but other applications of the heterocycles in other fields also. So we have worked on the wide variety of anti-cancer agent, like anti-anxiety agent or anti-hypertensive agents. We have published a large number of papers and number of review articles on this. And fortunately, our papers have been, they have been cited by a number of the workers. So in this case, we have also used the multi-component reaction strategy, then sustainable construction of various bond-forming reactions, then catalytic CH activation and functionalization, and basic focus is on the selectivity-based approaches, that is involving the regio, chemo or distereo selective approaches. Then we have also worked on another very important field that is development of new fluorine-containing building blocks for more discovery of the new pesticides, herbicides, and CNS agents. Then inorganic compounds and materials for catalyst innovation. Then testing for these compounds for this anti-corrosive optoelectronics, anti-malarial, antimicrobial agents. Especially we have done extensive work on the development of superbugs. If time permit, I will go into this detail. Then we have also developed we have used the nanotechnology in the catalytic processes and optimized the synthetic methodology for metallic and carbon-based nanomaterials, graphene oxide. And recently, few papers have been published on this upcoming field of development of graphitic carbon nitride and applications of these nanomaterials for the synthesis of value-added materials, the development of pharmaceutically important heterocyclic moieties, and then recent focus is on the photocatalytic nanomaterials for visible light-induced organic synthesis and dye degradation. We have done extensive work we have done in the field of this organic synthesis, heterocyclic synthesis, and bond-forming reactions. But today I would like to focus on the multi-component reaction approach, which is also called as the domino synthesis, and this is the MCR. As compared, for the beginners, I would like to mention little about the multi-component approach. In normal reaction approach, we do the stepwise synthesis. The reactant A is converted into the product B, then C and D and off, like this sequence of the reaction. As you know that insulin is having, I think, 150 number of steps. Synthesis of insulin involves 150 steps, and mostly synthesis of all the molecules normally requires more than 4 or 5 or large number of steps. But in case of multi-component approach, this is the convergent approach in which we mix together the various reactants in a one pot and give the energy, and then it is converted into the product. So this multi-component approach, also called as the domino synthesis or the tandem reaction also, it involves the generation of complex molecular architecture by multi-bond formation in one pot reaction. It is very rapid and efficient for library generation. Diversity can be achieved simply by varying the reacting components. It eliminates the need of purification steps. That is very important thing. So it is easier to work with the sensitive or unstable intermediates, and naturally, from the green chemistry point of view, it will save on the cost and amount of the reagent, solvent, and reduce the amount of waste that is generated. So actually, we are working in the field of green chemistry using the various tenets or using the various procedures, following the various principles. So we have used the alternative energy sources, ultrasound, microwave, infrared also, because less information is available in the infrared, which this infrared reactor we have developed indigenously in our laboratory and reported the reaction using the infrared for the first time. And now we are also focusing on the use of UV visible light for carrying out these organic transformations. The wide variety of alternative reaction conditions have been used, either solvent-free synthesis, neat reaction, or polymer-supported reaction. Then alternative reaction media using the ionic liquids, water, ethyl lactate, sulfate, carbon, supercritical carbon dioxide, fluorous solvent, we have tween 80, PEG, etc. But in today's talk, I would like to focus only on the two solvents, water and ethyl lactate. Then we have used the alternative catalysts, wide variety of green catalysts. But since, as I came to know that most of the participants are either beginner or the students, so I would like to focus simply on a very simple table salt, sodium chloride. How can we use these very simple reactants or the catalyst or the reaction enhancers to make the reaction very economic. And we have also used wide variety of nanotechnology, means nanomaterials. If time permit, I will go into the one or two. Then synthesis of magnetically derived nanomaterials, then graphene oxide, graphene-based materials, graphitic carbon nitride, and so on. So these are some of the recent publications in this field in which we have carried out the work in the last 5 or 10 years. And this our paper published in the Bioorganic and Medicinal Chemistry has received the award as best paper and most cited paper by the Elsevier. Then another paper, Tetrad Letters, is one of the most reviewed, most viewed and downloaded papers. Some papers are published in the Green Chemistry, which is most having the highest impact factor in this field. Now this impact factor has become 10.5. So today, what I would like to focus is to study the approaches for the synthesis of medicinally and industrially imperative heterocycles. So I would go into the detail of heterocyclic synthesis and organic transformation in aqueous media and using the nanocatalysis practices and their use in the field of biological screening, use as OLED and corrosion inhibitors. So water is very interesting solvent. Actually, mostly the organic reactions are carried out in the presence of organic solvents. But organic solvents are volatile, flammable, causing the various health issues. So recently, the more focus is on the water, and Professor Chakravarti has already told about the importance of water in the last lecture. So I would not go into very much detail of this, but we have also used the water as reaction media in some other manner that I am going to tell you. So water is having the high hydrogen bonding, high dielectric constant, causing the solvation, high specific heat, low viscosity. But water cannot be preferred for the organic reactions because of the poor solubility of most organic compounds in water. So to overcome of this problem, we have studied the hydrophobic interactions in heterocyclic synthesis using the water, which is the nature's reaction enforcer. Because the main motivating factor to carry out the reaction in water is that when all the complex reactions in the nature can occur in water, why can't we carry out the synthesis in water? So we have to find out the various ways. So for this purpose, we have studied for the first time, this is the first report, for the use of common table salt and combination of these two for the development of sustainable combination for organic synthesis. And we have studied the reaction which are less explored in the water. So we have used this water in aqueous media, water using the sodium chloride for the synthesis of novel spiro derivatives, which is the very interesting molecular architecture having the various stereogenic center via 1,3-dipolar cycloaddition reaction, which is one of the very well-known reaction of organic chemistry, and very, I think this is maximum studied reaction for the generation of complex molecular architecture. So this, when we studied the reaction of these three easily available starting material or the synthone, when reaction is carried out in water, no reaction occurred. But when we use as the sodium chloride as the reaction enhancer, and reaction was studied at 80 degrees centigrade only, then this product, you see that beautiful design product has been obtained. And this is the first report for the 1,3-dipolar cycloaddition reaction of azomethene elite and in the aqueous medium. And this reaction, since only one product is formed, so only one diastereomer is obtained extensively in quantitative yield, although more than one stereocenter is present in the cycloadduct. So reaction proceeds with high degree of selectivity, regio, chemo, and stereoselectivity. And reaction is very simple to operate. Just mix these three reactants in the particular ratio and the sodium chloride in a particular ratio. You can see, go into the details in the paper, which is already published. And simply by heating at this temperature, we can convert this product reactant into the product. And the structure is naturally, it is very difficult to assign the structure. So it is confirmed by the single crystal X-ray picture. And this, we have synthesized the combinatorial synthesis of more than 50 compounds. As mentioned in the last lecture, the drug discovery process involves the development of either the lead identification or library generation. So more than 50 compounds have been synthesized, and this has been scaled up to develop the 10 grams of compound. So these hydrophobic interactions, as we know that these water molecules, because of the hydrogen bond, they form these cyclic structure. These are called as cosmotops or clathrate type of molecules. And because of this hydrophobic nature of organic molecules, this ring structure, clathrate hydrate model, is proposed due to formation of these cosmotops around these organic molecules by hydrogen bonding in the water molecules. The reactants become separated And because of the separation of the reactant, they cannot reach to each other, and the result is reaction does not occur solely in the aqueous phase. While to develop the sustainable methodology, this new idea we have used, and this we have checked the use of sodium chloride in the water. And why we chose the sodium chloride? Because it is inexpensive, environmentally benign, and volume of the waste is significantly reduced, readily available, can be removed from the reaction mixture by aqueous workup. And we, in our case, we could obtain this final compound by the salting out effect. And results were published in the Green Chemistry. Later on, we have extended our studies because normally the referees have commented that it may be by chance for this particular type of reaction, but actually we have extended our studies, and some other interesting results were also obtained using the sodium chloride in aqueous media. So what happened when sodium chloride is added into this reaction mixture, then sodium and chloride ion competes with the organic reactants for the water molecules. And due to the strong interaction of these ions with the water molecules, they won the competition with the reactant and perturb the cosmotrophs. So this causes the migration of the water molecule from cosmotrophs to the ions, which turn break the water cage and significantly enhance the hydrophobic interactions. So as a consequence, more space is generated for reactant-reactant interactions, and the reaction occurs smoothly and desired product is formed. So this wine-3 dipolar reaction, actually as mentioned by Professor Chakravarti, that if we use this phase transfer catalysis or quaternary ammonium salts, then the reaction can occur in water. But in our case, the reaction is retarded rather than accelerated. And this is the result of the fact that purely hydrocarbons, dyeing prefers the interior of the micelles, whereas the more polar dienophile resides on the average in the head group region of the aggregates. And this spatial separation result in the modest inhibition of the rate of the reaction. Further, by the addition of the D2O, reaction is decreased due to the isotope effects. Now, this reaction can be carried out easily using the tap water. No need of use of distilled water, milk water, or any other. We have studied the various type of cations and anions to study the role of this. Instead of sodium chloride, we have taken some other salts, but the best results were obtained in the sodium chloride in tap water in just 40 minutes with the high yield. So this methodology is very simple. Operational simplicity is there in this particular reaction. So this can be used for even for the BSc or the MSc for the synthesis of this complex molecular reaction is very atomic because only byproduct is water and carbon dioxide, and it is environmentally friendly because this is gaseous, go into the atmosphere and water is separated. And now in this particular case, I would like to mention that importance of multi-component reaction approach. Now when these two reactants are added together, they first form the addition product, then immediately loses the carbon dioxide and form the ylide. And this ylide, if there is no dipolarophile, then it can immediately undergo the dimerization and converted into this beautiful molecule having the center of symmetry. Although this molecule is beautiful, but we were not interested particularly in this molecule. We were interested in this molecule. So to achieve our goal, this reaction we have tried in the multi-component reaction approach. So instead of going the dimerization, this is trapped by the dipolarophile and our required molecule is obtained. So you can see that by using the multi-component approach, how the different products can be formed under same reaction conditions. The regioselectivity of the product was also explained in our paper. I would like to just give you the bird eye view of different works which we are doing in our laboratory. So this will motivate our students and some new beginners, that is in the laboratory of the state university with the limited resources and even the limited funding. How can we do the good quality of work and publications? So we have designed these various beautiful molecular architecture for the first time, having the various stereogenic centers synthesized by this methodology, and then their structure, naturally very complicated, difficult to establish, was further confirmed by the single crystal X-ray picture. So library of the spiro and dispiro heterocycles have been synthesized. You can see that beautiful structures. So importance or highlight of this particular reaction is high distereo selectivity, formation of more than 3 chiral centers. This reaction is endo-specific, generation of spirocarbons with attached functionalities, one-pot procedure with the formation of multiple bond, diversity-oriented synthesis of number of compounds with structural complexity, high atomic economy, and one of the most important thing is metal-free synthesis, avoiding the harsh conditions. So another important thing, this is recently in this year also only we could publish this paper, and this is again the first report on this particular development, in which we have used the ethyl lactate and water as a mixture for the synthesis of these molecules. As we know that one of the traditional method which is present in even the school level chemistry or higher chemistry books or etc., the alkynes can be converted into carbonyl compound by using the mercury and large excess of concentrated sulfuric acid. It is very well-known traditional method. And carbonyl compounds are very important synthone for the development of value-added materials or the pharmaceuticals or the fine chemicals, very important from commercial point of view. So this methodology, which is very old, it is not suitable from the green chemistry point of view. And it also leads to the formation of the mixture of the product. It is not very selective. So several methods have been developed, modified to achieve the synthesis of carbonyl compound. Metals, various metals, acids, catalysts, ligands, and additives were used, and they have shown the low regioselectivity. But in our method, we have converted these alkynes, aryl alkynes in the carbonyl compound selectively using the ethyl lactate and the water in the ratio 1:3. Reaction is carried out on 110 degree. So in this case, this is metal acid catalyst ligand additive free Markovnikov hydration reaction. This is simple and highly efficient, excellent regioselectivity, environmentally benign catalytic solvent system, broad functionality, group compatibility, suitable for commercial purpose also. Now the formation of this product using the ethyl lactate and water without using any catalyst or any strong acid, this alkyne conversion into carbonyl compound is explained. This reaction was studied for the first time and recently reported from our laboratory. The hydrogen bond network in the ethyl lactate and the water mixture plays a crucial role and decisive role in activating the alkyne for the hydration to afford the corresponding methyl ketones. Now you can see that this ethyl lactate and water can undergo the hydrogen bonding, and 3 types of complexes are possible. First, in which the hydroxyl oxygen atom is involved. Second, in which the hydroxy hydrogen and keto oxygen atoms are involved. And third complex, in which the keto oxygen atom is involved with the hydrogen bonding with water. Now the various theoretical studies have been done, computational studies have been done to see the structure of the complexes and to find out which complex is more stable. And it has been observed that this complex formed by this complex 2, which is the most stable, and it is taking part in the reaction, and the Griffith's free energy profile calculated for the addition pathway based on the energy values of the transition state and energies of the product. It can be inferred that the Markovnikov product is both kinetically and thermodynamically controlled instead of anti-Markovnikov product. So on the basis of this theoretical studies, calculation of the energies, effect of various factors, it has been proposed that the product will be formed involving the complex 2, and actually it has been found that the theoretical studies are in agreement with our practical studies. So interaction energy calculations we have summarized in table. They have shown that complex 2 is most stable among the 3 complexes with energy of interaction is lowest. And you can see that in this case, particularly complex 2, intermolecular hydrogen bonding between the hydroxyl hydrogen and keto oxygen group of ethyl lactate with water. Through the above calculation, as I have told, the complex 2 was the most contributing hydrogen bonding network in the mixture. This hydrogen bonding network activates the water molecule, brings it in extremely close immediately to the phenylacetylene molecule for the hydration reaction. And these hydrogen bonding interactions predominantly exist in the high water concentration as compared to ethyl lactate concentration. That's why we took ethyl lactate and water in 1:3 ratio. So this is the mechanism. So because of this complex formation between the ethyl lactate and water molecule, they come in these complex again undergo the hydrogen bonding formation with the alkyne molecule. So these two come in close proximity. They activate the acetylene molecule for addition of water, and initially the addition water takes place, enolic species is formed, which undergo the tautomerization to form the ketone in the first step. So reaction was studied under various reaction conditions. The hydrogen bonding network is between the ethyl lactate and water molecule interact with alkyne, while hydrogen bond donor acceptor interactions, and brings the water molecule in close proximity of the alkyne to form enolic intermediate. The subsequent tautomerization of enolic intermediate gave the final product. Now, to further confirm the reaction mechanism, we have added the radical scavenger, so which did not affect the yield of the reaction. It rules out the possibility of the radical mechanism. Then reaction is also studied in the inert atmosphere. An excellent yield of the desired product was obtained, which ruled out the probable involvement of any oxidative pathway. And when we use the D2O, then lower yield of the desired compound is obtained because less effective hydrogen bonding relative to that of H2O. And further, this test shows that both the hydrogen atoms participate in the reaction, because any association of the hydroxyl group of the ethyl lactate molecule direct to the phenyl acetylene is ruled out because only deuterated product is formed. So by these extensive studies and proposal of the mechanism, this simple reaction has been carried out, and again the reaction conditions are very simple. They can be easily operated in any undergraduate or school laboratories also. And this scope of this reaction is the alkyne hydration reaction for the production of alpha beta unsaturated carbonyl compound through the reaction of aldehydes with alkyne as ketonic surrogates. Normally, these alpha beta unsaturated compounds are generally formed by the reaction of aldehyde and ketones, but in this case, no need of pre-synthesis of ketone because these alkynes act as surrogate for carbonyl compounds. So using the water as reaction media, we have published large number of papers, and these are some very important publications which we have done using the aqueous media, water as solvent. So if anybody is interested, can go through these publications and know the various details. Now coming to the another part of my talk because for the interest of the students, I would like to share some different approaches. The nanotechnology, you are very well familiar with the nanotechnology. That is, nanotechnology deals with the structures size between 1 to 100 nanometers in at least one dimension, and it involves developing or modifying the materials or lattice within that size, studies in that size. So can you imagine about the nanometers? That is, 1 nanometer is the length of 10 hydrogen atoms, and diameter of the human hair is 50,000 nanometers. Although this is the era of the nanotechnology and the boom is in the field of nanotechnology, but it is not new field. The medieval artisans were the first nanotechnologists who made the stained glass by mixing gold chloride into molten glass. And optical and electron properties of the gold nanoparticles are tunable by changing the size, shape, surface, chemistry, and aggregation. In very old like forts and the palaces, especially in the Rajasthan, these more than 1,000 years old, these molten glasses are available, these glass, so they can see this. They knew that by putting very tiny amounts of gold and silver in glass, they could produce the effects found in the stained glass windows, and you can see the old like windows of these stained glasses. Now, what is special about the nanoparticles? Nanoparticles exhibit different properties than larger particles of the same substance. They exhibit size and shape dependent properties, and surface area to volume ratio is very high. So there is drastic changes in the various properties like the electrical properties, optical properties, magnetic properties, and so on. And you can see that the aurum, which is yellow in the color, when it is in the nano size, this color is changed, showing the change in the optical properties. So applications of the nanotechnology is everywhere, but I would like to focus on in the field of catalysis. As mentioned earlier by earlier workers, that nanocatalysts represent the bridge between the homogeneous and the heterogeneous catalysts. They have the advantages of both. They have the high activity, high selectivity, excellent stability. They can be easily separated from the reaction mixture, energy efficient, and they have the atom economy. So based on this, we have synthesized wide variety of mono or hydrometallic nanomaterials, magnetic derived nanomaterials, polymer supported nanomaterials, and graphene based nanomaterials. So nanomaterial synthesis can occur in by various methods, physical methods or biological methods or the chemical methods. But we have followed the co-precipitation methods, especially, or chemical reduction or chemical oxidation, and especially we have focused on the co-precipitation methods. The selection criteria for the nanomaterials should be, it should have the variable oxidation state, cheap, non-toxic, abundant, highly stable, because of their special properties, and we have also published several review articles on this nanocatalysis. So actually, the sustainable development requires the key knowledge of all three: material science, the green chemistry, and the nanotechnology. At the interface of these three, if we work, then we can develop the best sustainable methodology for the development of value-added materials. So today I'm not discussing these monometallic nanomaterials, which we have used for wide variety of name reactions and bond forming reactions of nitrogen containing heterocycles. And then for the precise modification of the catalyst surface by introducing another component could facilitate the controlled tuning of the catalytic properties. So for that purpose, we have synthesized the metal decorated graphene based sheets, which can be easily separated by the filtration. Then we have developed also the magnetically separable nanoparticles. They can be removed, separated just by using the external bar magnet. Then we also synthesize the polycarbonated metal nanoparticle composites. They can simply remove, they can be removed by the application of the forceps. And these nanomaterials are, as usual, characterized by these various methodology. And naturally, for the selection of nanomaterials, we should take care of this toxicological categorization of metals and also about their cost. So I would like to focus today only on the era of the graphene-based material, because this is the era of the graphene-based material which involves the magical chemistry of carbon. Although we have also worked on the graphitic carbon nitride, but because of the shortage of time, I think I would not be able to go in that. So graphene-based material are very important. This is the crystalline allotrope of carbon with two-dimensional structures. A thin flake of carbon, just one carbon atom thing. Material is completely new. It is not only the thinnest, but it is the strongest, good conductor of electricity, excellent conduction of heat. So graphene-based materials, there are carbon nanotubes also, but in case of carbon nanotubes, there is less number of Ag carbon, or rather there is no Ag carbons, while in case of graphene-based material, there is highest ratio of Ag carbons. So they provide higher and special chemical reactivity, and in this graphene-based material, each carbon atom is in exposure for chemical reaction from two sides due to 2D structure. And further, this partially reduced graphene oxide is also used for the various purpose, because in this case, the monomolecular sheet consists of the carbon, oxygen, and hydrogen in variable ratio, which is obtained by treating the graphite with strong oxidizing agents. It is low cost as compared to carbon nanotubes, and it possesses the various acidic functional groups, and its acidity is high, having the pH of about 4.5, and possess anchoring sites for the disposition of metal nanoparticles. Because of these various sites, various functional sites, these metal nanoparticles can be anchored on these sites. So graphene has been used in the various fields, and I will go into the detail of only one or two applications. Wide variety of these nanomaterials have been immobilized on the graphene instead of carbon nanotubes. Today I would like to focus on the graphene oxide or reduced graphene oxide. These are the various approaches for the synthesis of this catalyst. Either the top-down approach, which we have used in our laboratory using the graphite, or it can be bottom-up approach using this simple starting material, then polymerization and growing this polymer. And then we have developed this modified Hammer's method for the first time, using the hydrogen peroxide as oxygen instead of using the potassium permanganate, and hydrogen hydrate has been used as reducing agent. So in this case, the protection, reduction, and functionalization occurs in one step. And these metal nanoparticles which we have used in the same pot prevents the restacking of the graphene sheet, also avoid the irreversible agglomerization of graphene oxide. This part we have published in very good journal Analyst, and these are the wide variety of these metal decorated nanomaterials we have developed in our laboratory. This cerium oxide that decorated material is developed, and it has been used for the first time in the organic synthesis. Like copper oxide is again used for the first time in the organic synthesis, and europium oxide derivatives also for the first time. Then silver derivatives, although very low, well known, but we have studied some new synthetic reactions for this purpose. Then characterization has been done by these various methodology. So because of shortage of time, or I can't go into the detail, now I would like to focus on this molecule. You can see that this is very beautiful, complex architecture. These molecules, these are having the methylene bridge. And methylene bridge bicyclic systems are called as Trogger's base and DN targeting fluorescence system. So encouraged by this molecule Trogger's base having the methylene bridge, we have designed this molecular tweezer-like compound. Because of its presence in the very well-known anti-malarial artemisinin and other important derivatives, so designed this molecule and we have developed the cerium oxide decorated this reduced graphene oxide sheet. And this is very interesting story again, because we have developed the this catalyst for the first time, while the earlier reported methods were polymer complex process, precipitation approach, supercritical synthesis, hydrothermal methods, flame spray methods, reverse micellar synthesis for synthesis of these derivatives. But we have synthesized for the first time by the solution reduction method for this cerium decorated graphene RGO sheets. And then they have studied for structure has been established by this various studies. And this catalyst is very important for other applications like the automobile exhaust system, oxidation ion conductors, and other studies. So in this case, we have studied the aqueous mediated multi-component approach for the synthesis of this complex molecule. You can see that this is, we again, as I have selected only those reactions which we have carried out by multi-component approach in one pot. One pot, these readily available starting material, these are commercially available of very low cost. These synthones or starting materials we have used in using the cerium oxide, this nanocomposite in the aqueous medium under microwave irradiation. This compound is synthesized in one pot. It involves aldol condensation, Michael addition, bicyclization, and it is chemoselective without using of any volatile organic solvent. High turnover frequency of the catalyst, which is very important in case of catalytic studies. It is possible for the recycling and economic viability of the catalyst. So in this case, you can see that structure of the molecule is again, we have to confirm by the this single crystal X-ray picture. It involves a formation of one carbon-carbon bond, two CO bond, two stereogenic center, two hexacyclic ring with bridge head structure were also there. And these molecules have shown the very interesting biological activity. While the previous methods were multi-step synthesis using the hazardous reagent with high temperature, non-compatible solvents, and always formation of mixture of compounds and unavailable starting material, which those scientists have developed in their laboratory. So this result were published in the molecular catalysis, and this reaction was to optimize the reaction condition and to check the suitability of our catalyst. We have studied the wide variety of other catalysts, and this, instead of the nanomaterials, the bulk material was also studied, and the reaction was compared. And it has been observed that under microwave irradiation, taking these three reactant in this particular 2 millimolar ratio, the reaction occurs very smoothly in aqueous medium. And to establish this reaction, because we have proposed this reaction sequence for the first time, to establish the reaction mechanism, we have also carried out the reaction in the stepwise manner to confirm the mechanism. And it has been found out that either the path A involving the reaction of 1 and 3 can occur, but it leads to the formation of other products. If the path B is followed, then reaction first takes place between 1 and 2, and then it undergoes the aldol condensation, and it will follow this reaction entire pathway to form the required product in one pot. So again, this type of nanocatalytic reaction sequence we have utilized for another type of petasis reaction which is attractive methodology for preparation of large variety of compounds. Then also total synthesis of steroids and various other derivatives have been synthesized for you applying this metal decorated RGO for these particular type of reactions. These are the mechanisms. I'm not going to detail. So we have studied wide variety of nanomaterials that is decorated on the either the graphene sheets or RGO or graphitic carbon nitride. The starting material for graphitic carbon nitride was melamine, and which can be synthesized very easily in the the MSc laboratories. Some who are interested, they can go through my publication, recent publication 2021 only. And then another important catalytic derivative which we have synthesized is polycarbonated zinc oxide nanoparticle composite. Now in this case, polycarbonate granules are weighed and dissolved in the dichloromethane. Then zinc oxide nanoparticles, which were synthesized separately, were dispersed in the solvent using ultrasonicator, and then addition to this polycarbonate solution with stirring for 30 minutes. And then solution was poured into flat bottom petri dish floating on mercury to ensure a uniform structure of this membrane. And these were then characterized, and these nanomaterials have shown the very interesting catalytic activity, and it can be synthesized for the substituted alpha beta unsaturated compounds exclusively instead of the bis chalcones in case of cyclic ketones in the regioselective manner. Then another is synthesis of magnetically separable copper ferrite nanomaterials. This methodology is very simple. It is sustainable protocol, simple, economic, facile, room temperature synthesis heterocycles can be done, magnetically separable, almost quantitative or attractive alternative to the filtration and centrifugation. It enhances the reusability, and it can be used for the industrial application also. So in this case, the copper ferrite nanomaterials were found to have the inverse spinal structure, magnetic property were superparamagnetism. So because of superparamagnetic behavior, it prevents the self-agglomeration since they exhibit their magnetic behavior in only when an external magnetic field is applied. Now these nanomaterials have been used for synthesis of these molecules. Now, manic reaction, it is one of the most studied and one of the oldest reaction of organic chemistry. So this is a new story of new studies of old story. So we have studied this particular reaction. When this reaction is carried out conventionally, it results in the formation of this manic type of product. But when we studied this reaction using the copper ferrite nanomaterials in aqueous ethanol at room temperature stirring for 3 hours, then instead of getting this product, we could obtain this very interesting molecule, and these are the very synthone for the drug used for the treatment of lung carcinoma. And this hexahydropyrimidine ring is present in number of pharmaceuticals. So this method is excellent. As I've told you, recyclability of the catalyst, high atom economy, because only the water is here. The water is formed as a byproduct. Operational simplicity, shorter reaction time, just 3 hours, and easy handling. And again, for this unexpected reaction, we have explained the mechanism. Double condensation takes place, and this product is formed in exclusively. Its structure is confirmed by single crystal X-ray. And this catalyst, after the completion of the reaction, can be easily separated by this external bar magnet, and catalyst can be used for more than 3 rounds, and there is no leaching of the metals in the product, because which is the essential when these compounds have to be used in the pharmaceutical industry. Now coming to the another, because I think Dr. Baboon, can I continue?
Madam, you can continue till another 5 minutes because Professor Osit Chakraborty sir is also waiting. He needs another 10 minutes to conclude his lecture.
Okay. Anyway, so another photolytic reactions, photocatalytic reactions, we have done extensively, and I would like to, we have used this photocatalyst for this dye degradation, for the, we have done extensive work on the band gap engineering, and we have studied visible light induced dye degradation using the copper oxide nanoparticles decorated reduced graphene oxide. Various dyes which we have used, because in the Rajasthan there is a big problem because large number of dye industries are there. So this project was given by the state DST and we could achieve the success in this goal. And then we have also used this for the synthesis of heterocyclic compounds. Then we have explained the mechanism
Dear participants, I think we lost the Professor Datia Madam because maybe due to some connectivity issue, maybe connection disrupted. Yeah, Professor Osit sir, can you please continue and end your lecture? Because
Right, I'm sharing my screen. Huh?
Yeah, yes, sir.
Is it visible at your end?
Yes, sir.
Yeah, so what we found out that these are the disadvantages of the existing procedure, and we thought that it can be made a much greener way, particularly if we can use oxygen as a sole oxidant. So the reaction, but what you have to do, you have to use a activator. Like in other cases, we found out that simply passing oxygen gas to the reaction mixture does not help to capture the hydrogen, because you have to activate the molecular oxygen, and NHPI in catalytic amount was used to activate the oxygen, and the reaction works very well, and we could get a very good acylation procedure. So the reaction proceeds via the triple or maybe triple CH activation at the methyl group, and also one CH activation at the sp2CH activation, so that the benzylation taking place. So to have a dig out in the chemistry to prove that it is a CH activation procedure, a CH KSKD isotopic effect studies were done. Initially, by the classical way, people do it by proton NMR analysis method, isolating the product and doing the ratio. By this time, since we have developed a very good expertise in utilizing mass spectrometry in various ways, particularly reaction mechanism determination, we thought that if we take a mass spectrum guided KSKD study, that is going to be a proper quantification and exact entity we can identify. And so MS guided KSKD also gave a reasonable KSKD isotopic ratio, telling that it is in fact going via the CH activation protocol. So this is the way. Other things are more or less known, how exactly palladium catalyzes the CH activation. The things which were not known earlier, that how exactly the activation of the methyl group is taking place. So this is the role of the NHPI. So it make the corresponding PINO or radical, and then it abstract the proton hydrogen radical to generate the benzyl radical, and now the oxygenation takes place, so that ultimately it proceeds via the aryl radical. This aryl radical undergoes that oxidative addition to the palladium 2 species to make the palladium 4 species, and then the finally annihilation transposition takes place. So to prove that the reaction works, it requires the presence of oxygen, and that the reaction proceeds via radical pathway. We did a study that if the reaction is performed in the absence of oxygen, particularly nitrogen atmosphere, you do not get the desired product. Similarly, if the reaction is performed in the presence of a recognized radical quencher like tempo 1.5 equivalent, normally people take 10 equivalent of the tempos. We found out that no, 1 to 1.5 equivalent is enough to show its radical nature. So the reaction proceeds via the radical pathway. So now with the methodology on hand, so what we did, we have correlated the various functionalized moiety over there initially by using our methodology to introduce the aryl group. In some cases, the yield is not more than 70 or 80%. In those cases, what we do, we take the classical condition, that means tetramethyl hydrogen. Particularly when this aldehyde moiety is functionalized with a heavy alkyl group, then we found out that we have to resort to the literature procedure. So both the procedure we generated all the various possibility of the modification. So the catechol moiety can be either in the aryl side or the catechol moiety can be in this ring. So in the original molecule, it is in this ring. So with this, we have done the PD4 inhibition studies, and we have a larger number of compounds showing more than 80% inhibition of the PD4 B2. Now we have to see the PD4D selectivity, because if it is non-selective to D, then or selective to B, does not inhibit the D, then only the side effects can be minimized. So things are at this stage now. So after doing this, we have to find out the IC50 value, whether it is better than this or not, and then we can think about that which molecules should be put to the animal studies. So this is the discovery. Now I quickly take you that in the development part, particularly aqueous chemistry, how it can be used for the application of the water-assisted synthesis of the drug molecule. So we're interested in this molecule because this is a apparently simple compound to treat the cardiovascular disorder, and it has been approved 2001. But it offers a new approach to treat the angina pectoris. So that is the reason that this is a target molecule, and it was approved in 2006 and launched in the same year in the US market. But what attracted us, that when we are doing the patent search, the lot of patent was coming, most of them US patent, couple of US patent from our Indian pharma companies. And when we went through the patent, we found out the majority of the patent, all the patents, they are dealing with how to minimize the impurity. None of them are actually the process patent. So we thought that if people get a patent, US patent, out of simply minimizing that how and what they're doing, they're taking different methods of purification, maybe the solvent combination changing, the chromatography method is changing for that. So if this is the gravity of the situation, then why not to think about a completely new process, so that is going to be much, much more creditable. So this is the target molecule. We have gone through all the reported procedure and we understood where is the problem. So problem is that where you are introducing the this part of the molecule. So in the most of the cases, this part of the molecule is introduced in the early stage, and that is the cases you are generating the impurity, because that is the major source of the impurity generating. So we have revisited the synthetic procedure, and we realized that by this time with our knowledge that each and every step the reaction can be performed by water, except one case where we have to take probably the ethyl alcohol, which is the next best solvent. So this is the entire step is actually being promoted by the water. So it is an improved synthesis of the ranolazine. Naturally, we have patented also, and the patent also has been granted. So to prove that the reaction proceeds only by the water, whenever we claim any water-assisted synthesis, if the same reaction can be done by any other organic solvent, we do not claim it. So we try to prove it. So a much concise synthesis was done later on, which is a completely different pathway, only two-step synthesis. So it provides a 77% overall yield, whereas the reported overall yield is not more than 30%. So it is a leapfrog jump with reference to the overall yield. And we found out that what you require that to introduce the piperazine moiety, which is the essential pharmacophore, we have to take N Bock protected piperazine, otherwise you get a double impurity of the product. So we felt that you need not to take the Bock protected piperazine so that you can avoid the deprotection method, provided that you can control this thing in such a way that only one molecule is going to be hooked up, not like that both the nitrogen atom is going to be acylated. And here also we found out that reaction in water, but you have to take capital ammonium iodide. This is not a oxidant and etc. This really is a solubility enhancer, 10 more %. Then we have a selective monoacylation reaction, and then subsequently the reaction works. So here also overall yield is much than the reported overall yield. So the reaction works very well. So the first step of the synthesis is the acylation reaction of the starting material. That can be done either by the corresponding chloroacetyl chloride or chloroacetic anhydride. We found out that chloroacetyl chloride, the reaction gives a moderate yield, but chloroacetic anhydride gives a very good yield. So to prove that the reaction is not catalyzed by any trace amount of the metal impurities, we have carried the reaction in tap water, pure water, and this is ultra pure water, means it is a ILGA purified water. So there is no metallic impurity, no microbial impurity present there. And as you see that when the solvent has been replaced by the classical organic solvents, so practically you do not get the desired products. You get more than equal amount of yield in tap. So the reaction can be far from the tap water. And we realized later on that chloroacetic anhydride undergoes hydrolytic side cleavage. So that is the reason we get only 45% yield over there. So then we thought that if we are taking chloroacetic anhydride, then half of the molecule is being lost. So that means atom economy is defeated. So these can be only if we can make the reaction work with chloroacetyl chloride. So here we found out that in the presence of the surfactant, here also it is nothing called oxidative precipitation. It's merely it is truly a solubility enhancers. And with S-DOS, you can get an 80% yield, but that yield can be improved to 90% when we take a minimum amount of water. We found out the water amount should be not more than 5 equivalent with reference of the acetyl chloride. Then only you can use only 1 equivalent of the chloroacetyl chloride. So the reaction works very well. Having sorted out this thing, that we have made the total synthesis. The second molecule is another molecule. It has been approved by the US FDA in 1990s, but what was found out that apart from the desired biological activity, this happens to be working with a large number of drug targets. So this might be a perfect molecule for the repurposing. And there is, at the time, there was only one patent in this molecule. There has been no Indian patent. So we thought this is the right molecule to take up for the process development. So here also, we re-engineer and find out. Yeah, actually, in other previous cases, all these things are actually water. Here, in one step, we have to take ethanol as a solvent. So the reaction works very well. The first step is going to be the epoxide ring cleavage reaction promoted by water, and the second is an aromatic nucleophilic substitution reaction to introduce the benzoyl moiety. So these are the two critical steps of the reaction. And here also we found out that a different route can be done with a much concise way. This is the step where the reductive amination reaction, you have to take a non-hydroxylic solvent, otherwise the catalyst gets decomposed. It is still stable in ethyl alcohol, but ethyl alcohol is the next best to water. So this, but except one step, all the step reaction has been promoted with the water. So herein also that to prove that this is only promoted in water and no other solvent does the job. So you see that this only water at room temperature, 10 degrees centigrade temperature, it gives a 80% yield. And this might be the role of the water, the hydrogen bond formation with both the amine as well as hydrogen and the epoxide. And this hydrogen also, so that it gives. Here is a 2 molecule of water molecule provides probably the best way to activate both the electrophile and nucleophile. So this perhaps the role of the water molecule. By this time, a lot of other people also have given a dimeric water molecule or trimeric water molecule are normally involved. The second critical reaction also, we found out that this only in the reaction works in water, no other solvent works. So here actually 3 water molecules. So we have taken this is the way it can both activate the chlorine, this nitrogen atom, and this nitrogen atom, so the reaction works very well. So we found out the completely all water synthesis for this drug molecule. Dr. Dandi has talked about a nanocatalysis. So nanocatalysis is provide a distinct advantage. So we thought that is it possible to get extraction of the advantage of nanocatalysis as well as an aqueous media? And we had an opportunity because we found out this scaffold happens to be the scaffold A, a versatile scaffold, because this represents a large varieties of therapeutic molecules, like from CARP expectorant to the adrenergic blocker, which is a cardiovascular agent. But the chemistry involves a opening of the suitably designed glycidic ester, which is an epoxiding of the glycidic ether by a phenol. So we had a lot of works earlier that epoxide opening reaction by amine. We have a lot of catalyst also in this figure, but amine happens to be a little bit a better nucleophile, and phenols are very poor nucleophile. So that's the reason it does not work very easily. And the time we are looking about this chemistry, we found out these are the handful of methodology available. The most effective was that gallium bimetallic complexes. It takes a very costly gallium catalyst, and it also requires a preparation also is not commercially available. So we found out that is it possible that we can polarize the epoxide bond by a palladium nanoparticle. By this time, it was known that sulfur lone pair electron can be polarized by a gold nanoparticle. But gold nanoparticle is a softer nanoparticles. But since sulfur also is a softer side, so that's the reason gold can polarize the sulfur nanoparticle. Since this is an oxygen harder side, so we thought that we have to take a harder nanoparticle and palladium. We have screened a various of catalysts, and we found out that palladium nanoparticle is going to be the effective for that. So this is the condition that we take palladium chloride, 25 mole% of the potassium carbonate and 25 mole% of the tetrabutyl ammonium bromide. It equals as a capping agent. That means it does not allow the agglomeration of the nanoparticle. So this is not merely a base promoted reaction, because one would anticipate that initially it is going to make the phenoxide anion, and phenoxide anion is doing the job. When we treat it with an one equivalent to the phenoxide anion, under a if we do not take any tetrabutyl ammonium bromide, then the reaction does not take place. So it is not merely what we call that potassium carbonate is acting as a base and it is abstracting the proton. So here what is acting, potassium carbonate is acting as a reducing agent in the presence of water, so that the palladium 2 is going to be reduced to palladium nanoparticles. So we have done all the TAME study and to prove that it is a palladium nanoparticle and the site. But we found out that the reaction works only when the solvent is aqueous media. So in other solvent also, yes, a palladium nanoparticle formation takes place, but yes, a size varies. So, but we do not get any trace amount of the formation of the desired product. Only the product formation takes place in aqueous media. So here tells that you need the palladium nanoparticle as well as the aqueous media also. So to fit their role in the mixture. So this is the way perhaps through the transition state 1 it is going. So palladium nanoparticle, they activate the epoxide. And this is the role of the water molecule. So water molecule through hydrogen bonding activates the epoxide also through hydrogen bonding. This is the hydrogen bonding, and also it is going to activate the phenolic moiety also through hydrogen bonding. And then it is bringing the phenolic OH group pretty close to over. So we have detailed study. So one would expect that if it is a nucleophilicity driven, then if you take a phenolic moiety having an electron withdrawing group, this is going to be poor nucleophile, the reaction will not occur. But we found out the phenol having a electron withdrawing group works in a competitive way or alone also in a much better way, so that it is not the phenolate is being generated. If there is an electron withdrawing group, the twofold advantage takes place over here. Number one, it will undergo hydrogen bond formation much effectively than without having an electron withdrawing substitution or having electron donating substitution. But perhaps the more contributory role is coming that once the palladium nanoparticle activates the epoxide oxygen, it actually make a 8, like it becomes negatively charged. And that has to be stabilized. And this is taking place of back donating of the electron density from the metal center to the pi cloud. We have not claimed it because our objective was different. This is the first or earliest example for anion-pi interaction. There has been a lot of studies And the present director, Dr. Nara Sastri of IIM this Jorhat, who was earlier in IICT. So he has written a review article, this cation pi interaction. So anion pi interaction is very less numbers are there, and this is the earliest example of involvement of anion pi interaction. But since our objective was different, we didn't highlight it. Now we realize that one we should have very much protected to have mentioned that. So the reaction works, and all the drug molecules can be synthesized comparatively in some cases better way, and most importantly, the optically active molecule does not lose its chiral purity. So since it is a important molecule, the naturally whatever we do, we try to protect it in the patent. So this also has been patented, and the patent has been granted. Now Nitor Mohali, because now since I have superannuated, but there is a very good active patent cell. So they are working with the industry about these two processes, the analogy process and this unit process for that. I think some people have showed interest, but not many industry people are still keen to take up the philosophy of the green chemistry. They are still bothered about the price comparison, which they are doing. So I think that's the last structure. So what I tried to do that all the new chemistries you call environmental benign or aqueous mediated reaction, ionic liquid integrated, spoke to talk to you in this regard, or particularly new chemistry which has been developed last couple of years, nanocatalysis or the CH activation. But the purpose this new chemistry has developed, particularly in organic chemistry, ultimately purpose is their usefulness in making the drug, new molecules, or the process chemistry. And as has been commented upon by 2016 Jamaican paper, that where have the new reactions done? So they have given a sensitization to the medicinal chemists, use those new chemistries in the not only in the process chemistry but also in the discovery chemistry. To this effect, we try to incorporate the aqueous chemistry, but before doing that, we try to put a light on the aqueous chemistry, that why you should be encouraged to use water as a solvent. What is the distinct advantage you might think about to extract? In this regard, we said that in majority of the cases, depending upon the interacting ability of the reactant with the water molecule, it might provide you assistance through amphiphilic dual activation. And this is an conceptual advancement in understanding, as we suggested with the same philosophy, these two science papers could establish their thing, and it has been highlighted, this particular NBOC formation in the 20 years collection of the organic letter, which tells you that how much important it is not merely a water mediated reaction, it goes beyond that, its implication. And we have utilized the aqueous chemistry and developed a lead molecule, PDE4 inhibitors, and again for the purpose of looking for a therapeutic agent to treat asthma and COPD. And in this regard, we have optimized the lead of the PDE4 inhibitors by really taking advantage of the late stage functionalization of the CH activation. We have developed the chemistry, and the same chemistry we have utilized in true sense for the late stage functionalization for a speedy generation of the active molecules, and we have got better activity. Only thing is that it is to go for the PDE4B and PDE4D selectivity, and then only 3 molecules will pick up to the IC50 value, because IC50 takes a lot of enzymes, and these enzymes are recombinant enzymes. It is exported for that. It takes a lot of time to take one kit. And in terms of the process chemistry, we have found out the novel all-water chemistries for the greener and more effective process for the ranolazine synthesis, and also all-water chemistry for the protecting group synthesis of the lubulizole. Both of them are new way to treat the cardiovascular diseases. And of course, we have tried to extract the double benefit of the nanocatalysis as well as a water medium for the epoxide phenolysis, which generates a platform technology because it provides a versatile pharmacophoric scaffold and its application towards the drug synthesis. So what I try to put upon you that there is no doubt about that the modern life depends upon the development of the chemistry, petrochemicals, or the chemical industries, but it appears that the processes following which those commodities are prepared, those are not as sustainable in terms of the resources and the environmental impact. And green chemistry principle aims to tackle this problem, and real progress has been made in various other aspects. So, but generally it is undermined. Always there is a criticism, and the undue criticism is that yes, you are basically replacing diethyl ether and etc. But to sensitize you that the green chemistry is not merely just simply you replace the chloroform and diethyl ether by the water. It is an innovation and discoveries of new chemistries and not merely incremental improvement of traditional synthetic methodologies. The word green in green chemistry refers to fresh, young, and new, and this has been coined by none other than by the father of green chemistry, Paul Anastas. And I think by establishing the molecular level role of the water and identifying the actual catalytic species through mass spectrometric identification as a proof of concept, we try to prove that one, that yeah, it requires a lot of scope in innovation. And by exploiting the same concept well activation, we have extended this methodology, this concept water catalysis for the synthesis, much effective way for the all water synthesis. In ranolazil, all the steps are water. You do not take any organic solvent, even in the purification also, and we have made a completely impurity-free process. And except one step, which is a reductive amination reaction, it has to be done in a non-aqueous media, and alcohol is allowed the next best solvent. Ranolazil synthesis also has been done in a much more effective way. So both of them involves innovative chemistry, and same thing is applicable for the dual activation role of the nanocatalysis and the water for the platform technology. And now, not all the students. So actually, two students who actually initiated our water means like N-Bock formation reaction. Shune, he is in the discovery in the AstraZeneca in the Switzerland, and he is their main person in the medicinal chemistry. Another person who is a thermochemical reaction who did it, this early to work, was Rajkumar. He is a professor and dean in the Department of Pharmaceutical Sciences, Central University Punjab, Bhatinda, which is about 4 hours driving distance from Mohali or the Chandigarh. That nanocatalyzed, and Dinesh and Damodar, where is Damodar? He is now entrepreneur. Dinesh is now an assistant professor in NIPR Ahmedabad. They did that all water chemistry for the ranolazil synthesis. This lady now settled in USA, Naisargi Parikh. Initially, she started the reaction in the master's project, and then she did the PD for work. So she has actually done that S-DOS catalyzed reaction. I didn't talk about his work, although he has been involved in the epoxide phenolysis reaction with the nanocatalysis. Sudipta Raharai is in Delhi IT, assistant professor. And the CH activation actually or nanocatalysis in a more elaborate way has been exercised in my laboratory by Dr. Kapila Seth. He is also the assistant professor, Department of Medicinal Chemistry in NIPR, Guwahati. There are many other students who has contributed, like Rajesh Chebulu. I could not talk about his chemistry, which is basically a hexafluoroethanol chemistry, the same thing. And Anirban also, he's a lecturer in a college in West Bengal. He decided to stay back in West Bengal. He didn't go for postdoctoral abroad. So he also has done ionic liquid catalyzed reaction. And most importantly, thank you for your attention. As I mentioned, all these chemistries are done in this nice institute, NIPR, Mohali. Currently, I am in this institute, Indian Association for the Cultivation of Science, as an emeritus fellow. Just recently, I have shifted. After superannuating from NIPR Mohali, I decided to stay back in Punjab, because I served Punjab for more than 25 years. So I got used to the Punjab environment. So I shifted to IIT Ropar, but I came in early 2020 for a family function, and I could not dare to go back over there. So I left that place and tried to relocate myself in Indian Association for the Cultivation of Science, Kolkata. So I think that's what I thought that I'll share with you, and I'll be happy to interact with the inquisitive mind. Yes, Dr. Banerjee, I am through.
Thank you so much, sir. Thank you so much. Though there's some interruption regarding this internet, but we must learn this thing from you, because though I belongs to this generation, but I am totally surprised to see the reaction of our generation. Maximum participants want just certificate, but still you means it. I'm very much happy to see the potential at this age also, and for this subject also. So thank you so much, sir. Actually, Professor Ansu Dandia madam is still waiting.
Yes.
Our lecture also. Thank you so much, sir.
Sure.
Thank you so much.
Sure.
Thank you so much, sir, for your nice presentation. Thank you so much. Now, Dandia madam, can you please unmute yourself and please carry out your rest of the lecture. Tanya madam, can you hear me? Co-host. Okay, ma'am, I think we need to make you co-host. Please, yeah, now you can, yes, ma'am.
Yeah.
Sorry for the interruption. Now, please, ma'am, you please finish your lecture. Thank you, ma'am.
Yeah, can we share?
Yes, ma'am. You please share, right? Nice to see Sarah also.
Oh, yeah. Is it visible?
Yes, ma'am.
Okay, I will not waste time too much. It's because we are already late.
Okay,
But I would like to share this very interesting work.
Yes, ma'am.
It's very short. Actually, recently we have done this reduction studies, avoiding the use of metals, hazardous acids, or reducing agents, high temperature or pressure. And then we studied metal-free photocatalytic reduction process using the eosine, graphene oxide, and ammonium oxalate using the isopropanol and visible light. Our process is very simple and highly efficient. Superior photocatalytic activity due to the synergistic system of eosine with graphene oxide and ammonium oxalate. It avoids the need for inert atmosphere, which is generally needed in common reduction process. It is broad surface applicability. It is metal as hazardous reductants, additive-free selective photocatalytic reduction, environmentally benign system. Excellent chemoselectivity is also observed when the carbonyl compounds are having the different other reducible functions or electron donating or withdrawing group present in these molecules. And this method is suitable for the commercial production. Now, in this case, this simple metal-free, sustainable, environmentally benign catalytic process was developed. Eosine is used as photosensitizer, and the graphene oxide nanosheets are used as electron relay mediator, ammonium oxalate as hole scavenger, and isopropanol as a proton source without employing any toxic transition metal containing nanoparticles and complexes, use of any hazardous reagents, and employment of stoichiometric reductant. As we know that in case of most of the reduction reactions is either carried out by using the molecular hydrogen or by using the metal hydrides like lithium aluminum hydride or sodium borohydride using the high means constant reaction conditions and using the high molecular stoichiometric ratio of these reducing agents generating the huge amount of waste. While in our case, there is no need of all these things, and by simply taking these things in a very particular ratio, we can carry out the reaction very easily. Now in this case, we have optimized the reaction condition and found that this methodology developed by us is suitable for wide variety of aromatic aldehydes having the various electron donating or the withdrawing functional groups or other reducible functional groups like heterocyclic aldehydes and other aliphatic aldehydes, etc. They can be converted very well, very easily in a high yield, more than 95% into the corresponding alcohols. And this synergistic system of graphene oxide, ammonium oxalate with eosine, could significantly assist the separation of charge carriers and consequently improve the rate of the reduction reaction of carbonyl compounds. No metal hydrides, no hazardous chemicals, no need of high stoichiometric amount of the reductants is needed. And recently we have received the acceptance letter from the Green Chemistry journal. Now in this case, what happened? The first organophotoredox catalyst eosine was excited by the visible light from ground state to excited state to form photo-triggered species and photo-reduced for this and produce photo excited electrons and holes, electron hole pair. So single electron process takes place, then these absorbed electrons are used for this conversion, absorbed on the graphene oxide surface owing to the outstanding electron accommodating and shipping properties of this GO nanosheet. Simultaneously, the photo generated holes in the valency bond of eosine are trapped by ammonium oxalate to increase the charge separation or resist the fast recombination of photo-generated electron hole pairs, and contributes a distinct role in this photocatalytic reduction reaction. Now this, in the next step, the activated benzaldehyde receives 1 electron from GO. An aromatic benzaldehyde radical anion species is formed via this single electron transfer process, and the resulting species is quickly trapped proton from isopropanol to give the Y-active species. Finally, again, the electronic trapping from graphene oxide and proton from the isopropanol biosine intermediate gave the desired product. So this is a very important contribution, and in this case, we can see that without using the molecular hydrogen or high pressure hydrogenation, which is very risky to be carried out in the MSc or laboratories, etc., this process can be very easily carried out in any laboratory. Although we have done the reaction using the photoreactor, using the xenon lamp, but simply when we put this reaction mixture in the sunlight by using this mechanical stirrer, the reaction goes very well and we can separate the resultant product. So this is especially suitable methodology to be used in the undergraduate or the postgraduate laboratory. So we have synthesized a wide variety of these value-added heterocycles, and they have shown very good corrosion inhibition activity. They have been shown the very good biological screening activity, and because of shortage of time, I can't go into the details. They have shown the anti-malarial beta-hemetin inhibiting activities and antioxidant properties, antiviral, etc. And these activities have been done in collaboration with the CDRI Lucknow and Microcare Laboratory Surat. And these heterocyclic compounds are particularly very important for the application as OLED because they have electron-rich centers. So they have the significant potential for the development of these organic light-emitting diode materials. And these studies we are carrying out at various centers. So this are number of publications, although recent publication of 20 and 21 are, I think, not shown in this. 20 and 21 are not shown in this, and we have published huge amount of work using these nanoparticles and RGO, and recently graphitic nitride have also been used. So in the conclusion, we can see that these development of chemo regio or stereoselective synthesis is useful for the generation of high value chemical entities. Parallel synthesis can be carried out for the generation of library of the small molecules, which is very important in the pharmaceutical industries. And we have also developed the green synthesis of nanocatalysts with well-defined structures. Then improved selectivity is obtained by the nanotechnology. Nanocatalysts with vast surface area are more selective and efficient in carrying the synthesis. Based on economic standpoint of view, nanocatalysts are much more inexpensive than conventional catalysts, and we have designed easily recoverable and efficiently recyclable catalysts. Then we have also used the eco-friendly tandem approach for rapid organic synthesis without efficient functional group transformation or functional group protections. Techniques reveals of high special efficacy for the development of sustainable technology, and they have the distinct advantage of more selectivity in approach and final outcome. So I would like to thank, these are all the more than 50 students have done PhD under me, and some students are working, and I am really thankful to my research scholars. They have celebrated my 60th birthday in a grand celebration manner. And I'm also thankful to my motivators, great scientists, Professor C.N. Rao, Professor Govardhan Mehta, who have given me various awards and motivated in various ways. I'm also thankful to this IUPAC president for giving me this International Women, Distinguished Women Scientists, this president of CRSI giving the bronze medal, then this MHRD ministry for giving the best chemistry teacher in India award, and so on. I would like to invite all of you to our Rajasthan, which is very famous for the various heritage, various sports and palaces and heritage. So I'm sorry because of all these disturbances, but there's a lot to tell. I'm thankful to you for your kind attention and bear with me for this shortcomings. There are so much to tell you in so less time, but something I tried to communicate you by this today, that with the small laboratories, with the limited resources, if you want to do something, you can do that, and you can get the good publication, and also the funding can be obtained. Thank you so much for your kind attention.
Thank you so much, ma'am, for your very informative, and I think we must learn the attachment with chemistry still you have, and maximum participants, and because of this 141 participants, around 139 participants are still present. So just planning to organize another international conference with bioactive heterocycles. So definitely we will organize another international conference, and definitely we will invite you again to explain the other biological aspects of your synthesized molecule in that conference. So dear participants, if you want to share, yeah, 2% raise hand. Yeah, please share your. Please start video. Yes.
So this is Ashish Mathuri from.
Yes.
This is Ashish Mathuri from Niger, Bhubaneswar. Thank you, ma'am, for nice presentation, and I'm very appreciated for you for different water as a solvent in medium, reaction medium. That is very beautiful scenario in chemical reaction. And just one inquiry: when you use in last green chemistry paper, when EOCNOI and graphene oxide, and then they are combined to form the cationic and any mechanism. But I told you EOCNOI, I think this mechanism a radical type mechanism, but why it is called cationic or anionic mechanism? Any?
So it is photocatalytic reactions, so it involves radical mechanism.
Ma'am, how you can prove this is the radical mechanism? Any radical trapping experiment this type of
when we use the tempo, that is this sensitizer, by using this, we can confirm the mechanism whether it is radical or it is an ionic mechanism.
Actually, ma'am, we can try. We are trying this when material and EOCNOI both combined together. Then how it is prove and tempo. Then a different adduct formation. We cannot detect any radical.
Possible? Can you send me the details? I have given here my email ID and mobile number both. So you can send me the details, and then we can discuss in detail in length about your problem.
Ma'am, thank you. Now another participant, Deepankar Jena, please.
Thank you, ma'am.
Yeah, we will discuss in detail. I can solve your problem, I think. So you kindly send me the mail, your information by mail.
Yes, sir. Can I say now?
Yeah.
Yes, Bobun sir, a very good evening. I am Dipankar from Balasar, Odisha. So I have no Kori madam, Angshu madam, and Asit sir. One thing I want to say in this platform, I will take the 30 seconds. We must learn something. Out till now, we have attended about 11 dynamic lectures by almost all professors among their as per best, as I have learned within 2 days. But thing is that we must see that Asit sir and Angshu madam, in their age of what is their age, but what is their energy? It's just not energy in their slides. It is their energy and commitment towards this internal seminar or internal conference. We must learn from them at the age. If they are so committed, we are just in her age of student. We are 30 35, we are in the just age of student, but we are very bored with 2 to 3 hours of a constant class, taking class or learning from the class. But how they are committed in their age, I am really grateful, and I am praying to the Lord Jagannath madam and Asit Kumar sir that you must stay with happy and peaceful and long life. You are the energy of the society, madam. Many teachers teaches us, but some inspires us, and you are for me, both of you. Now I can say all of best, but Asit sir and you are from them for me. I must pray for all of you being the good health, always being happy. I am very happy that such type of international seminar able to interact us with such type of personalities. Educations are always there in our life, but persons make many different in our life. As my mother used to say, job is a matter or work is a matter. It is up to you. It is very person to person. So I'm so happy. I'm so happy. I'm really thinking the gray hair of sorry sir, Asit sir. But what the energy? Green energy with gray hair. It is fine. It is really fine.
Thank you and God bless you.
Thank you so
Sir.
much for nice compliment.
Thank you, Dipankar. They have that potential. That's why they are in their position.
Really, sir, we have to learn many things from them. Yes, sir.
We must learn this thing at least. At least we must learn this thing. That's why I want to say something. Otherwise, last 3-4 days, I am trying to motivate other participants. Please join. Please try to listen. But it's okay. At least few, 100 student or 100 participants, if they are serious and if they are attentive, I am more than happy. And I think my entire hard work, I feel satisfied now. Thank you, Dipankar. Yeah, Amit Pandey, you want to say something? Yeah, Dr. Sasadhar Maji.
Yeah. Am I audible?
Yes, yes.
I respect Professor Asit Kumar Chakraborty sir and Dandiya madam due to their potential. Really proud of them. Ma'am, actually I have one query.
Yeah.
We have seen when phenylacetylene was treated with ethyl lactate in presence of water at 110 degrees centigrade, desired carbonyl compound was obtained. My question, have any role of terminal sp hybridized hydrogen atom to afford the desired carbonyl compound? Because if acidic hydrogen is replaced by alkyl or aryl group, your methodology is valid or not? Because in a conventional way, when terminal acetylene was treated with mercuric salt, such that mercuric sulfate or mercuric oxide, mercury 2+ cation was able to activate the double bond.
Sorry, Dr. Maji, sorry to interrupt you because it is a long question. I think so. Madam has already shared her mail ID. So can you please write that mail ID and then definitely Madam will answer your questions or queries.
Okay.
You please collect the mail ID, or if I can share you the mail ID. If you have any questions, you please contact madam directly. Okay, because it is already 5:53. So I need to stop this meeting here because madam is still from the first lecture she is attending. So I can share you the mail ID. You can share your questions with madam. Okay, sir.
Okay.
Thank you so much, ma'am. Thank you so much, Sri Chakrabarti sir. Thank you so much, and thank you. The participants still remains. You are the genuine participants, I think, and you still it is more than 100. So I am very much grateful to you, and thank you so much once again, Anshu Dandiya ma'am and Sri Chakrabarti sir, for your support and guidance throughout my career. Thank you so much. Thank you so much, ma'am. So, dear participants, we to stop here. We'll again meet at the last day, sharp at 8:45, and there tomorrow we have 5 scientific lecture and valedictory session at 4 to 5. Thank you so much once again. Thank you so much. Thank you so much, ma'am, and thank you so much, sir. Thank you, sir.
Dr. Bhuvan, don't
Yes,
get
sir.
disheartened that if there are 300 participants, only 100 people are attentive. So if per symposium you are being able to activate 100%, and suppose in 3 years you have 3 things, basically you are activating 300%, right? You don't expect 100% success. So
Yes,
it's a tremendous job. So it's a good thing that you are popularizing chemistry culture. So good. And thank you very much for
thank you, sir.
organizing this conference. And
Thank
all the
you.
best. All the best.
Thank you, sir. Thank you, ma'am. Thank you.
Thank you for giving me this opportunity to share my some of recent research findings with these young participants. And I will try to do my best. So if they have any query, they can directly contact me.
Okay.
Thank you, ma'am. Thank you, ma'am.
We are grateful, ma'am. Thank you, ma'am. Thank you, all the participants. So, goodbye for today.